I've been covering really very large patterns very deliberately, and many people ask me a question about being comprehensivist and then being competent, and what I've learned to do in disciplining myself is that I can go plunge in depth for various periods of time. There's something you really need to know about, and you really go after it and let nothing impede you. Having, however, started from as comprehensive a base as possible, I really never lose the fundamental comprehensivity, and I can come back really quite rapidly from any subject. For instance, there's a period when I really needed to get at the sanitation for dwellings, and I spent 2 years just developing a mass production bathroom. But I really did find a great deal, and just such simple matters that there was only one man in the United States making designing all the toilet bowls at all the different companies, and found there was nobody really knew why a toilet bowl was the way it was except this one man. And he'd inherited his art from some English craftsmen, and he was in a little top room in a building in Toledo, Ohio. And Standard Sanitary and Kohler and all of them were getting their information from him. And I found that in making the toilet bowl, so the tolerances that can be maintained between forming the original regular ceramics and again your clays, and then before you bake it, one thing and other things, a lot of weight. Things go out around, so you could not have any machinist kind of tolerance at all. If you hold to a quarter of an inch in diameter of opening, you're doing very, very well. And all this really became very impressive to me, so I decided to really go in pretty deeply, and I found no scientists had really ever looked at the plumbing. Just think what we're really saying is this is in our day. Scientists are not looking at plumbing. They find fault with the plumbing, they call the plumber. But nobody is asking scientists to look at plumbing, say that's, no, you're pure scientist, you mustn't be on this kind of nonsense. And here are all these extraordinary chemistries that are going into the toilet, and very valuable chemistries that are getting all pushed together. Nature is taking a lot of trouble to separate them out, and then we deliberately push them together. And when nature does separating out, if you ever get into mining or refining, you find it's quite a job to separate out. You spend a lot of energy separating out. So to deliberately let things go back together, it could not be more unintelligent. So I found that right in the very life of the people who are supposedly being educated to do logical things, right under their nose in their everyday life, they were missing things. So this called for a whole lot of attention. I did, I say, get deeply into. I found that I could produce stainless steel toilet bowls in 2 halves as stampings and get absolutely fine tolerances. I was able to, when we find out how many gallons of water we need to flush out the toilet, we find that people are getting rid of a pint of water and using seven gallons to flush it away. All this beautiful, valuable water coming down the hills that we need so badly. It all began to kind of hurt if you got in there deeply to see how much advantage could be found for humanity if you really got in. So it was very easy to get these fine tolerances, beautiful stainless steel and so forth. And anyway, the big point is that once you understand, you can be a generalist and plunge, and you really dare to pay no attention to anything else in science. Because I've been into so many different fields that plunge very deeply in many things, whether it's cartography, and when I do, there's maybe 6 months, 2 months, maybe 2 years that you're really off there. Then you come back in the big swing again. But there are a number of subjects which I have very good records of all these things, and so that there are a lot of slides, and I've just been really handling thoughts themselves, and I want to come back now really to artifacts and slides, and particularly to artifacts because I want to review for a minute with you my own grand strategy of how I carry on. When I made up my mind to peel off and commit myself precessionally to what had been called the side effects, but that is to really how to make ecology. You get on with ecology and play the game that life is trying to play, of making the big show work and not just looking out for yourself. When I did that, realizing there's nobody to mark your paper from there on, there's nobody to pay you, that only nature would support you if you're. My theory was if I was doing what nature wanted you to do, I'd find myself being supported, but be absolutely so indirect that you'll never be able to say this is for that. And that we must not get scared because it doesn't seem to be supported right now. Whatever it is, you must really keep on. And in doing that, I realized I must not waste any time. You're going to have to be terribly sensitive. You have to use everything that you're born with as a child, with intuition and sensitivity. Realize, am I really doing the right thing? This is where a child can really get in the forest. It gets to some critical point. We get to do things pretty carefully, so you can really be sensitive. So this meant then that if I had just my one lifetime to try to get somewhere, therefore I really have to get a whole lot out of my time. And I said, my experience tells me then that I've listened to a great many people talking to a great many people and trying to persuade the other that this is the way things are. And I made up my mind that people that I listened to were really not listening too much. They sort of wait for their turn to speak and sound off the. So I decided that what I would do, that I would discipline myself not to talk to people unless they asked me to talk to them. I've been in effect really asked to talk, and so that I'm talking to you because you're here to be talked to. Because I'm sure this is the only time really people are listening, but when they want to hear what you have to say, when they say so. So that became a basic discipline. And I made up my mind. Then if I was not going to use words, which so many people do use, as my prime approach, what else did I have? And I said, I see that nature is transforming continually, and it would be possible to, if we can comprehend the principles that she really is using structurally and mechanically, socially, really feel your chemistry, feel your technology, feel your hydraulics, pneumatics, electromagnetics, interattractions or repulsions. If you really feel those things, it'd be possible then for you to take, because nature is continually transforming the environment, that you can really participate in the environmental transforming. And the only reason that you're really doing what you're doing is that because you feel that you've discovered that this is why we are here for one another. And in a sense, you've already discovered that older people have very powerfully conditioned reflexes. It's not easy for them to adjust to the new, to take advantage of the new. They tend to hold on to the old. Therefore, I said my focus is going to be on not just looking out, but primarily on the absolutely youngest life that has no conditioned reflexes, and to try to give that youngest life, provide environments for that youngest life so that within which environment that child would prosper. Be one reason why you find me lying down, remembering how I acted when I was a little kid on a bed trying to get off the bed. I paid a great deal of attention to saying, inasmuch as there really are only a certain number of transformations, motions that I've given you, there really are, I find there are categories and really hierarchies of tools and no matter how fancy the tools look, there's pounding, there's pushing, and there's scraping off, there's the horizontals, the pulling, pushing and pullings. Things get down to really relatively few things that can be done. I said, I think that child, all the things the child is doing is very experimental, is finding how it can stand up. It is a superb research operation. And when that little child later on begins to tear paper, it isn't because the child is being mischievous. The child needs to know what coheres and doesn't cohere. You've got to keep testing things, because having been so informed, so consistently informed by gravity about falling, you must know what you can hold on to that won't come apart when you're falling. That's logical, isn't it? Because it has grabbed at the bed and so forth. Instinctively does that. So it's got to keep testing what holds together. So it's going to. You find they tear newspaper and that they're looking for things that look tougher. They tend to take your best papers. They tend to look at the things, try pulling apart things that people consider very valuable around the house, linen, so they might finally pull that apart. Finally, they find these things do hold. So I said, if you realize what it is they're trying to find out, it'd be very easy to really arrange things in their environment so they find the things that they need to experiment with, and they don't have to use a lamp cord to find out about tension. They can have another kind of a cord and be much easier to do it. So that the idea then was, how do you develop environments that are favorable for the new life, within which the new life can get all the information it really needs in the most logical way, and it doesn't tend to engender fear, that when experimenting, doing the things they are doing, something going to hit it in the head, or that the society is going to say, stop that, and find themselves obnoxious to society. I felt all this could really be done. So my first focus then becomes developing artifacts instead of words, and by artifacts and tools, I would mean a building is a tool, a great ship is a tool. So the artifact may be, I'm not talking about spoons and rulers and rather small devices, but any of the participation in using the principles of nature to take apart and reassociate and so forth. I'm really generalizing this for you very, very much, but the point is that I find that nature already has things in a certain association. She herself dissociates them gradually. She takes her own rock apart, and we could learn then how you take things apart. You find that they're very valuable chemistries that temporarily associate this way, that can be disassociated and reassociated in preferred ways. So that's what we do in mining, going around the world, finding there are certain resources, and then deciding where you're going to begin to separate that out. You've got ore. You have local energies available that will make it possible to do next steps of grinding or whatever you want to do. Or do you have to forward it in ships to get to another place where there are energies and so forth. There are many critical decisions made of that kind. But by and large, there's a very big pattern here. These metals are disposited very unevenly around the whole Earth. In effect, man goes halfway around the world and takes ore out of the ground and starts separating it. And as he goes along, sometimes leaves things behind. He separates and has the residues and keeps forwarding. And finally gets highly concentrated metals at various centers around the world. And as there's finally a maximum degree to which he separates these metals out from everything else, the chemical elements, then he starts reassociating them in preferred manner as alloys. And after that, we get to the point where things get to be made into special parts of special engines and so forth. And we begin to then we start assembling again in preferred ways. In other words, nature has come apart ability, she has reassociability, and you're simply participating in that in a big way. So I find that the total operation going halfway around the world to get the right metals, to bring them to certain concentrated places, while concentrating them themselves, separating them out, a lot of sorted, very valuable materials, and they start reassociating the preferred ways, whether it's going to be some kind of an engine or it's going to be some kind of a building, some other kind of tool. And then having gone into this very great complex undertaking, which is going to take months, it's going to take years to get those mines operating, the ships, it's a very big complex, taking a lot of time. And I got to then to demonstrate that all the time has been invested by man, all the energy invested by man, are going to be worthwhile having invested that way. So that what I have to do then is to arrange to get what you produced available to the most people around the world. So in effect, I now have produced something that's been assembled from all over the world. Now I must arrange to get what I have to all over the world again to make it most available to the most people. This gets to be the optimum big pattern that you're concerned with. I find then that if I do get it to the most people, available to most people, then we can find out very quickly whether was this really worthwhile doing, and how do you improve on it if if it's pretty good. And in the end, humanity ought to be gaining advantage. Humanity ought to be gaining advantage of greater health and more time, a little greater longevity, more freedom to undertake more things. We're continually trying to free up humanity from being locally preoccupied as a local machine. And to get freer to use more and more of its head, to look at more and more of the pattern, to be able then to be more and more effective with its mind, understanding principles rather than, and realizing how much more it could do with the energies that are available in the universe on the ends of levers to do the physical work, that we're really here to do the mental work. So that my total pattern then is halfway around the world inbound, halfway around the world outbound, which sum total is once around the world. There's a whole lot of energies that are involved. And I find that this makes it possible for me to get into a very discrete pattern. Next thing, I can really understand my totality and have a way of judging whether what you're doing is worth the doing. Such patterns I've just spoken to you about really are then highly documentable, what the Tao is involved, and make some very good calculation in advance whether this is going to turn out to be worthwhile to humanity. I do not look on these projects in the terms about whether people like the looks of what I'm doing for the moment. I'm always concerned with really how it works, and it usually looks all right because I'm concerned with not only how do you get it there, but how do you maintain it, and how do you in the end recover it, take it away when that becomes obsolete because you've done something better. So you get that in the recirculation. So I see a total responsibility in design, getting things to people, not trying to sell it to people, but trying to make it available to people. I'm very glad to be doing this program under the Bell service because one of the examples I use in industrialization, I consider by far the best example operating in the whole history of industrialization is the telephone service. That is, you don't try to sell people telephones. What you do, you're selling service. You're making it possible for people to communicate, and if you make it, the easier you make it to communicate and the more accurately they can communicate, the more people are going to use the service. So it's a very interesting matter. People used to think you've got to sell things to people because in order to get it improved, people they're going to demand a very good product. The telephone company learned that they didn't wait till people say, I don't know whether I can afford a new telephone. They didn't sell the telephone. They sold the people telephones, then they'd had telephone architects, and they'd had Napoleonic and Voodoo and Georgian telephones, and nobody could possibly sell the telephone to anybody else anyway. So the telephone company simply sold the service, and they found that every time they could find a little better way, they could really afford to scrap enormous systems because they could give so much more service that the number of people who use the service go up that fast. And so the telephone has continually been improved. So when I'm thinking about big systems and world systems, I find that this is a very good field to take working examples. I also then spoke about recirculating, using materials. The telephone company, when I was young, we lived just outside Boston. Our telephone number was number 10, so it was early in the experience of telephones. And it was not long, a few years before they began learning, you could get more messages over the same cross-section of copper wire. First we just one, and then began to get more, got up to 28, and then there was an increase as we went up to over 200. The next increase, I remember, went to over 1,100, then went up into some thousands. By 1930, the chief engineer of the Bell Labs said that at that time the telephone service was being employed by about 10% of humanity. So they'd be able to increase the telephone service so the whole world would be furnished with telephone service, and that during that time the telephone companies would neither have to mine nor buy another pound of copper. That during that whole time they would be copper sellers, because they found the rate at which they were learning how to get more messages per cross-section of copper was so vast that there actually was a gain. There'd be the amount of copper they already had was a copper mine, and it'd be adequate. That has turned out to be the fact. We have now one communication satellite weighing 1/4 of a ton, outperforming the transoceanic communications capability and fidelity of 175,000 tons of copper cable, 1/4 of a ton. This is the rate which there's suddenly this enormous step up, doing more with less. And my whole hope of how we were going to get all of humanity at a higher standard of living starts then looking out for the young life. You don't have to quarrel with them, because you give them something that really works, and that child, that's what he's going to use. And his reflexes are going to be conditioned to that which works, and that is what's intelligent. He won't have anything else from there on. And so that I said, it's a long pull job we're doing. We have to start with children, and have to get a whole lot understood before we could get anywhere. Because I found at the time I started what I was doing, people were thinking about architecture and buildings in such a powerfully conditioned reflex. It was just incredible that when in 1929, the first presenting that Maxine House to people, where I developed a machine for a living. It really was a machine, and using the most advanced technology we had, and I was able to do it to provide a 3-ton house. I was outperforming a 200-ton conventional residence. People, they were so taken up with Georgian, and so it was amazing, the conditioned reflexes, and how much is really in there, almost on a fear basis, because it goes back to the power structure and the castle. What the strong man has, the man down the street who's hiring your dad. So that's what he has. What he has. The people their eyes were just powerfully conditioned this way. So I had, in all the things I talked to you about, I want you to realize that I never allow myself to say what they're going to look like. I'm perfectly confident if you're doing it the right way, it's going to look strange. But in due course, people discover that is the way how things really work, and they begin to like it, because they can understand and feel it. As we began to get into space programs, the devices you see going off in space look very strange to people. And they didn't mind about that going off in space, but if it's something you're going to have around their house, you're going to have to live with, they've been very, very sticky about it. Now, I'm saying these things to you. I'm going to get into these strategies and a number of different projects I've gone into. But I want you to have a little feeling of the overall controls. I'm looking then at, as always, a world project. I'm looking at it total history. I'm thinking about the total inventory of all the metals of our Earth being separated out and progressively more easy to get out. And so I began to see them. There might come a time when you wouldn't have to mine anything. In fact, this copper is I also spent 2 years in depth in the Phelps Dodge Corporation as assistant director of research at Phelps Dodge, the third largest copper company in the world. And I really, it was there that I did also then plunge into doing some bathrooms and several things, and got into new types of automotive brakes using the steel we use. The steel is a very poor conductor either of heat or electricity. I got into conducting metals like the aluminums and coppers for the braking that carried off the heat very much more rapidly. So it just cut away from brake fade and more effective. And then I found I even got to, you could even have metal to metal. The Japanese had found that you had carbon brushes and copper together. The metal didn't get worn away, and they were using it for trolley with electric trolley going along to pick up its current and not getting nowhere. And I found I could get that into a brake. I developed in Phelps Dodge various things. I got in depth there. One was Phelps Dodge was primarily copper, but the gold and silver co-occur with the copper, and they also became very much involved with tin. And America and all the world was going to need a lot of tin in World War I. Tin ores coming from Bolivia, and get into low-grade tin ores. And there's lots and lots of low-grade tin ore. And there's a hard, something very difficult to separate out. And I found that taking the ground powdered ore, I was able to develop a centrifuge. And I had a centrifuge that had to be water-cooled so the metals didn't get to some critical heat where they break up, because when you get spinning great weights at great velocities, there's enormous tendency to come apart. So I wanted to introduce a very powerful flame, the blowtorch flame into the powder, and be able to centrifuge. So I had to design a completely water-cooled apparatus which just went on, so all the heat was just at the point of contact of this flame with the powder. And I figured that you might, like a cream separator, really be able to separate the tin out, because the weights are very much more. And sure enough, it worked. I didn't get that. They didn't get it into production. They were really very scared of the centrifuge, and that they might really kill a lot of people. But I did find it's actually possible then to take low-grade ores and centrifuge just like cream. And this tin was just running out. It was really beautiful. I've been able to get in quite depth in great many directions, and I've become very deeply involved with the metals and know a lot about their histories. And I would go into talking about that in due course. But I had made up my mind that this morning we'd go through some various slides, and I'm introducing to you a number of projects, some of them rather short, where I have really good slides of them. I want to take advantage of the fact that we do have something for you to visualize. And for instance, you find me getting into my map, and I was able then to develop a better method of projection and where there was no visible distortion. It was very important to be able to have a world map without any visible distortion. Because if you take the Mercator map and use the land as a background for, say, percentage of resources, or how many people are in that particular place, if the background is distorted, with Greenland 3 times as big as Australia on the map, but the actual fact is exactly opposite, then the relative abundance within that particular area is very misinforming. So I needed a world map that I could always, with absolutely no visible distortion, against which I could show percentiles of materials and peoples, whatever I wanted to see. So I needed to look at world all the time, so that's what brought me about my world map. And It is the only world map that is approximately distortion-free, both as to relative shape and relative size. So that brought me into a great deal of experience with the world map. Maybe numbers of times I've drafted the whole world, plotted the whole world on paper. It's been something so I've got. That's good for you too. As you go in depth, you get very familiar with the world. I found that there was something worth the finding, and what I found here was employed with the beginning in the space program. When you start and suddenly going into rocketry, and humanity is awed by the prospect and not at all sure how it's going to come out, and you start then experimentally sending enormous rockets in the sky to go great distances, people get to be quite apprehensive about where that's going to land and so forth. And so that I did make a discovery that there was a great circle around our world from America to America that didn't touch any other continent. And this would be a highly specialized kind of item, but you see North America there, and you see Florida where Cape Kennedy is, about here. And that Cape Kennedy, I've got an axis where you leave Cape Kennedy and you just miss South America, and you just miss Africa, and you just miss Australia, and you go over the neck of New Guinea, and you keep on going around, and you come back to Cape Mendocino in California, and then right back to Cape Kennedy. In other words, it was possible to find a range at which you could fire when you're not firing at the United States. I'll go around that once more, and it would be all right if one of you to come up and do something with me. Would you come up, dear? I want you to put your finger, if you sit down on the floor there, and we use this camera here, and put your pencil, put up your pencil somewhere, out just about there. I'm going to put this Cape Kennedy on there. You keep your pencil steady, will you, don't? And I'm going to do the turning. Okay. I just want to have it so you can see where it's pointing. See, it's just missing South America, just missing the tip of Africa. Or if I did it right, it would. I'll go back again. Just misses the tip of Africa, just misses Australia, and does go over the neck of New Guinea, and then comes right back to Cape Mendocino, and back to Cape Kennedy. Now, I have some slides of that, and it'd be sort of fun just to see it on the slide, because you can see the line itself. It's carefully drawn. That's a great circle. So it is the shortest way around the world. May I have the slides? It's quite interesting that in relation to that great circle, which misses everybody, what is south of it? By the way, look. Now you can see that line on here. It is north of my head is very much in the way there. It is just north of Florida on here. Now we'll turn the next picture, please. This one is just missed Africa, just missing Australia. Next, please. No, they're in wrong order. We see now where Alex missed left, just north of Florida, just going north of South America, and just south of Africa. Next one. Well, I've got some mix-up in my homework. I've done my slides badly. in relation to that line, and had an axis of it, because there's always an axis of a great circle. And it's interesting that see how many people are south of that line. For instance, South America is south of that line. And Australia is south of the line. And the Antarctic. So it's just Australia, South America. So South America has 4% of humanity. Australia has not 1%, and Antarctica is not 1%. So only 4% of humanity are south of that line. Which is 96% north of that line. Therefore, the pole, the north pole of that line, would be the nearest to the most people. And the north pole of that line is exactly, it's just it's in Russia, and it is just south of Volgograd, and that's exactly where the Russians send all their rockets from. In other words, they're sending it from the place that's nearest to everybody. I don't know whether they did any working on the geography about it, but it is interesting to me that is so. From the kind of work that I do, I often get extraordinary insights in what are the grand strategies of the big ideologies. And I think that I'm now going to come to the next slide. And there's the next slide, please. I'm changing my subject now, going off the map and that world strategy. Somehow or other, this set seems to be bad. You're looking at 3 rods on a tower, and the 3 rods pierce a vertical circle, and that's made out of a very high alloy aluminum strip. And so there are 3 hinges in that strip. There's a rivet at the point where the 3 rods come out through the vertical circular strip. Next picture, please. Now this same strip now has been depressed, and we see the rods still going through the 3 corners. Next picture, please. Go back. Can you go back with the pictures? Can you go backwards? Can you go back with that one? There should be 3 of those pictures of the rods in line. Let me just carry on. When we get to spherical trigonometry, now we're seeing the same circle of rods is a spherical triangle, which each of the angles are quite open, about 120. We've seen the same strip up high, then down in the middle of the equator. This is now a northerly great circle triangle, and the next one it was an equator, and then it was a southerly hemisphere spherical triangle. In other words, the same 3 pieces were transforming, and they went through a condition of 180 degrees at the middle. Now, I want to talk about spherical trigonometry, and we can let that go. You've all been brought up on your geometry with the sums of the angles of a triangle always 180 degrees. And I find people think that's just absolutely fundamental. So I'm going to have you go to the North Pole and take a great circle, which is a meridian. You now remember. When I use the word great circle now, I'm sure you go quite along with me to remember what they are. We take a meridian down to the equator, and at the equator, we'll then go 1/4 of a way around the Earth, and then we'll take a meridian back to the North Pole. Now, meridians impinge on the equator at 90 degrees inherently. So if I go around the equator, which is a great circle also, 1/4 way around the Earth, and I take a meridian back to the North Pole, I leave the equator at 90 degrees. I get back to the North Pole because I've been 1/4 way around the world. Here is 90 degrees at the North Pole, so I've got 90, 90, 90, or 270 degrees. This is a typical spherical triangle, and some of the angles are never 180. That's one reason why then I went through that model. Just, is it possible? Look at the spherical triangle you see. The same spherical triangle in the picture on your screen is now, those are 90-degree corners. Next picture of that, I can't seem to be able to get that series. There are three such triangles in the series, and they should. Now, there's the same triangle with the 120-degree corners. It's in the northern hemisphere, and the other one is in the southern hemisphere. And then one more, the middle one, where there's the equator, because at the equator, they're all 180 degrees. Otherwise, the triangles, the angles can get up to 180. So what we find then is the larger the triangle, spherical triangle, the larger the sum of the angles. As it gets works towards, I can make a, just take the equator then, that's 180, we've got a triangle that's 180 at each corner. Now I bring those same three rods in up just a little here, and the angles would be, say, 160 at each corner. If I bring it up a little further, they'd be 150 at each corner. And they will finally, as the triangles get smaller and smaller, they will approach being 60 degrees at each corner, but they're always going to be a little more. In fact, we discovered what you and I have been brought up as a plain triangle, as being normal, is the most extreme case of the most local, tiny little triangle. That's really very, very important for you to remember. As we were taught at school, a triangle is an area bound by a closed line of 3 edges and 3 angles. A square is an area bound by a closed line of 4 edges and 4 angles, all equal, etc. All the geometries that we learned about were areas that were bound by closed lines. That's the way the words were given to us. So that all we have credited about a triangle is what you see on one side of the line. There's a little area inside here. Now the fact is, I said you have to draw a triangle on something, because I'm going to be operational, remember. There's no, even if I say an imaginary triangle, I'm going to be imagining one I scratched in the ground. I continually will imagine a special case. I talked with Sonny Albright about this a whole lot last night, that while human minds are able to discover the mathematics of the generalized case, and though we're able to use the principle, we always have to use it, as I showed you the other day, objectively, in special case. And even even though we understand the principle, when we're imagining it, and I gave you conceptuality independent of size, we will always, however, make it into some special, when we make it conceptual, we make the dots of something, we make the points out of something, we tend to very quickly associate. We'll make it pink or something like that, in blue background if we think we're abstracting it. But you'll find that the brain has to use special case. Brain is designed for special case, and only mind has it. So the mind can say to the brain, think about conceptual triangle, but the brain will immediately make a special case. These are great nuances of exploration, but they're all coming out of operational procedure, and strictly to. So I say to a child, draw me a triangle. He said, where? I said, well, you got to draw me a triangle. So he said, I said, how about the ground, drawing the ground? So he draws in the ground. You're drawing 4 triangles. He said, no, I've just drawn 1 triangle. And I have to prove to him that he's drawn 4 triangles. So we're in Philadelphia here, And so he's drawing on the ground here, a little tiny triangle. I said, when you drew the triangle on there, you divided the surface of you did it on the Earth, and you divide the surface of the system that you did it on into two areas. You'll agree that if I make a circle around the equator, I divide it in northern and southern hemisphere, don't you? If I make the circle a little further north of the equator, I'll divide the Earth into two areas, a large southern and a small northern. If I get a little further north, it's smaller northern and larger southern. So the little boy has drawn a triangle here and divided the whole Earth into two areas. And both areas are bound by a closed line of three edges and three angles. So I said, you've drawn a very, very big triangle there, all the rest of the Earth here. And its corners, you think you got 60, the corners then are 60 from, they're 300 degrees each. It's a big triangle. He said, I'm not used to a triangle of 300 degrees. Well, I said, that's simply because your school made you so special and so absolutely myopic as not to pay attention to your environment. But that's really, we've got to really think of reality, and the point is you have deliberately done something to our Earth. You divide it into two areas. He said, I didn't mean to be the beginning. I said, you thought up to now that you were not responsible. Now you are responsible. You're doing that whole Earth. So he said, well, all right, you give me two triangles, a very big one and a very little one. Where are the other two? I said, concave and convex are not the same. And he's to prove that with the reflection of light, diffusing of light on one side and concentrating light on the other. And so there's always going to be a big concave and a little concave, and a big convex and a little convex. You've got four triangles. There's always going to be four triangles. I mean, our friend the tetrahedron, the accountability is there. This is that generalization of the tetrahedron as the minimum system in the universe, the minimum structure. And it can appear as that kind of a fourness. But they will always be there. There's nothing you can do without it being there. So we can say, I can hide away. No, the universe won't let you do this. Just thinking, I said, divides the universe, the outsideness, insideness. You didn't mean to do that, but you are immediately dividing up the universe. What right have you to divide up the universe? Well, you were given this special kind of capability in the mind. And so you can play with total universe, and I think it's going to be quite exciting to feel those spherical triangles and understand that, incidentally, if you do any of the mathematics of plane trigonometry are exactly the same for spherical, simply because plane triangle is simply an extremely limited case of spherical triangle. So the mathematics of the spherical triangle, really, there's not such thing as plane trigonometry. It's only spherical. And it's dealing with total systems and beautiful complementations of total systems. Now, so we say all you have to do is learn the spherical, and the plane is included. Give you the plane, and the spherical is not included. Again, the advantage is starting working with the whole of the particular. Now, something else I was brought up with in that schooling was being taught fractions. And the teacher taught me that I couldn't have, on top of the fraction, elephants and peas below. You had to have elephants both top and bottom in a fraction. You could not fractionate dissimilar phenomena. So that all felt fine. That seemed logical. Till we came to trigonometry, and they suddenly began to give you sine and cosine. So listen, what are those words? And show it to me. So I can't really show it to you because it is a ratio between two. It's a ratio between this edge of the triangle and this angle. So a ratio is a fraction. So suddenly they were giving me elephants and peas, and that's saying it's logical. One reason trigonometry has been difficult to people because they insist on trying to equate seemingly dissimilar phenomena. But if we get into spherical trigonometry, in no trouble at all, because we then realize that the edges of the triangle is simply the arc of the central angle of the sphere. So you have central angles and surface angles, all angles. So your fractions are entirely between angles. That comes very simple and nice. It gets to feel pretty good. In other words, The way trigonometry is taught, you absolutely automatically cut the kid's feelings right out. You say this is something not like, these are sines and cosines. They're exempt from the elephants and peas. This is when they say mathematics is something abstract. I mean, forget about all those models. These are the disconnects that I talked to you about, and I'm trying to find how do we get back to the conceptual and to the exact experience so that humanities can understand all of science, and they can. The more you play with what I'm talking about, the more fun you're going to begin to have. And you're going to find it's very easy to take ping pong balls and begin to try out great circles on them, and they're nice to. What the diameter of the ping pong ball is, and then you get a little, like a napkin ring that's just half of that, just the radius in depth. You stick the little ball in it, and then you just draw on the circle, always a great circle. So you make the ball all different, so you get any 2 points and just connect those points and get a lovely great circle. You're going to find a great deal of fun to play with great circles and have concentric triangles and see the way in which the angles begin to decrease. The little man then trying to start with a flat earth and squares and cubes, he said it is great. And just looking at the inside of the triangle, inside of the square, looking nothing. What we do there is teaching him to be absolutely biased. My side is right. My town is inside the wall here. This is incredibly unbalancing to the little child to be exposed to such bias. I hope you feel more and more with me the sense of responsibility to the child, that little child starting out here, and how easy it was to give them misinformation, and how easy it was for parents just loving their kids to pieces to say, well, that rich man got this tutor and he must know it, so we get that tutor, and the tutor tells it his way, and it may be very ignorant. And how quickly conditioned reflexes develop about who is authority about what. But the minute you begin to do your own thinking and go back to experiential basis of things, you can't get fooled. And you continually get better information. It's just so exciting, the lovely, clean things. You suddenly, every time you get understanding instead of something you memorize, some little local thing you memorize. Isolated from other things. And the globes used to be always fastened and things. I kept cutting them loose and finding, because you always set a globe into a circle. As long as the circle is a lesser circle, it's just always so comfortable there. So sit on any bowl, any dish, and so on. So you can have your globes and really get feeling your whole earth. I suggest to all of you that have plenty of globes around and begin to get on seeing things this way. When I developed my first map was in the 30s, and Life magazine published it in February 1943. They were a year or so getting ready to do it, and we went through some very interesting experiences. The art editor of Life was a great friend of mine. In fact, I'd been on Time and Life, so I knew everybody there, and it was just after I left Life that they decided they'd like to do my map. The Life magazine didn't want to go into something like that without being sure that this wasn't something as well known to geographers long ago, and just sort of rediscovery. So they got two great experts. One was Dr. Boggs, who was the geographer of the State Department, chief geographer of the State Department. The other was a man who was the president, the chief cartographer of the American Geographical Society. And they got two mathematicians. All of the experts said to the Life magazine, this is what they call, they said, pure invention. A very, I didn't conform to any of the well-known mathematics. Therefore, obviously, it was some kind of a fudging out. So the invention meant just sort of fudged. Somehow I tricked everybody. So I have a wonderful patent attorney. He was considered at that time the best in America. It was way back in the 30s. And he said, that's wonderful that we have the great experts testifying as pure invention. Because the chief patent examiner of the United States Patent Office had ruled in 1900 that it was impossible to patent anything cartographic anymore, that all the mathematics had been exhausted, so that it was taboo and never considered. So I got the first and only patent on a method of projection that had been granted in the United States Patent Office, out of all these experts saying it was pure invention. Isn't this great? So anyway, the Life took heart and decided to publish it anyway, and we published it in color, and it was a great hit. As Life and those big magazines do publish to get out a dummy a little head, they get, if it looks like a good one, the advertisement, they had 18 pages of color, and you could paste the edges together and put together. So I'll never forget the Sunday when I had to come out. The war was right on, it was deep in there, and I went from Washington to New York that Sunday, and all around the streets I saw kids going around with these gloves. It was an unprecedented number for them. They went to 2 million. They never had any such issue before. Well, Henry Luce was very excited that they're doing this. And there were 2 couriers coming from Australia going to Churchill in England. The 2 very especially, and they were just coming through New York, and Henry Luce was handling all the public relations for England in the United States, so he was very privy. These men came to him on their way to Churchill. And Henry decided he'd like to have my map taken to Churchill. He got the printouts before it actually published. So the couriers did take it. So the couriers understand how to show it to Mr. Churchill. I put the pieces together. And what I did was to put the pieces together with Australia at the center. If I could have I just moved my map in place here. It was very much the water-ocean world as you see it here. But I made Australia actually the center of it. And they say, gee, that's the way the world really is, isn't it? I just want to point out that the way things look to the local person, that is the way the world is. And then I showed them the other way it could be, and how they ought to put together Mr. Churchill this way, and they did that too. But all being exactly the same pieces, just rearranged. Incidentally, while Life was making up their mind about whether they would use my map, I'd made many, many drawings, and I had them all little cartoons and so forth. And Henry Luce asked me to come to his house in Westchester for the weekend. He had a number of guests. And after dinner, they asked me to explain my map, so I was doing it in the parlor floor, with people sitting around sofas, chairs. And Henry was sitting over on one side, and I was explaining many things from the map and grand strategies of different countries and history and so forth, the way the map tended to change with it. And Henry said, Bucky, every human being has an exact opposite. That's your poles, you have your antipodes on there you've been showing. He said, you're my exact opposite. I said, that's a very much of a compliment. And I said, how do you happen to give me such high position? And he said, well, you seem to think there's something going on in this universe. He was an absolute free willist. He was sure that, he said, anything I want to do, I can do. And you seem to keep introducing large patterns that are super to man. And they said I find this very disturbing way of looking at things. That he felt that all the big patterns are purely man-made. I was amazed that people in powerful positions can get to see things that way. He was used to enormous, but what his magazine could really do to people around the world gave him that feeling. Now, incidentally, I like Henry Luce very much. We were good friends for life, and one of the things that I had said at that occasion before the map was published was that there was a northwest spiraling going on of humanity, some totally, the centers of population are moving westward, if we took some total. There had been a time when men drifted east and rafts, but since the sailing business, everybody's really kind of trying to follow the sun. And it's quite easy to show that northwest spiral and how then Europe came into North America, and then goes South America, is going this north. And if you go into the map of the United States, there we have, you'll notice I have colors. And the color lines, I have the coldest is the blue, and it gets green, yellow, and the red is the warmest. There's a little line here from where you go between yellow and green. In the United States, it goes like that. And you see it here in where it may be. You see it going right through Europe here. That is the freezing line. That's where the average mean low temperature is 30 degrees. And so north of that line, you might get frozen if you didn't have clothing, for instance. If you're starting with a naked man, was a very formidable line at the outset. And I found that line was really, remember I've shown you pictures of where the people are. There was another one where I showed you little lights of where all the people are. But look around this where the enormous numbers are in here. This is where our population is. Find that people tended to get up as close to the cold as they could because the ice was good for preserving things, but you freeze to death. And also, the cooler, you got where there was less diseases, less infections. It seemed to be the sort of the health area. And humanity had tended to find that. Incidentally, when you get to mountains, there are rings around it. These are simply the sum total around the world. I didn't make separate rings with my colors going up the mountains. But they do have all those temperature changes, you know. So one of the things that fascinated me was the censuses of the United States since 1790. It's quite easy then, demographically, mathematically, to show where the center of population is. And the center of population of America has gone right from the very beginning, was right on that's 30 degrees mean low temperature. And so starting up here very much in Philadelphia area, and then goes southward like that, and out, and then out in the end down. It stayed always right along the line. But at the time of the Civil War, the population went just a little north of the freezing line. It had been just below it, following it. But Civil War is an amazing moment. This is 1851, production steel. For the first time, man had been doing his primary work really in the fields, and this is the beginning of the industrial, where he's able now to have environment controls, and he goes indoors. So he's able then to be a little north of that line. So there's a tendency to have the industrialization north of the line, as sort of started with beginnings of being able to get north of the line. Anyway, that is the tendency was still to get a little more northerly, so that I saw that the next population, I could really make predictions where they'd be, and they were working more and more northwest. So I also showed this to Henry Luce, and I said what had been called the British Empire that I've talked to you about as being British Empire, which I also shown you really wasn't British Empire, but really was the East India Company. That the East India Company that's the actual enterprise, the people who put their money in it. Where East India Company was a limited liability, where the individual risker could not be punished if somebody is suing the outfit. And we call that incorporated in America as LTD and limited in the English world. And the East India Company itself was moving west. The speculators began to move west. And I said to Henry Luce that in due course, this British Empire was going to be the economic controls were moving into North America. And I said that the English, whatever is English, that stays as English at all, is going to really move west. So I said they'll move their headquarters over into Canada in due course. Canada will begin to be strong, and you find this is where their investments are going. So he was very then I said he was an Anglophile. He was born in China. Went to Yale University, but he was born in China. His old China hand had feeling about the English in Hong Kong and so forth, and as I said, he was the official public relation propagandist for British Empire during World War II, and so he was concerned when I said the things were moving. There came a day, about 6 months after that map business, when he wrote me a note and he said, "Bucky, you're right. He said you didn't know this, but this occurred before the map, and he had heard me on these things before, and I made my prediction about the English in Nine Chains to the Moon, published in 1938, and Henry, while I was on Fortune between 38 and 48, this note came from Henry saying, "Buck, you'd be interested to know that the British had just sent their secret archives to Ottawa." And he said, "You really are right, but you didn't know the war was coming." And I said, "Of course I knew the war was coming." But the point is, how it occurs and why is irrelevant. All I say is, I'll say to you what is going to occur, but what are the actual critical factors that make it do? They're very happenstance. They're utterly unpredictable. The big thing is predictable. I think it's important for you to have some feelings of some personal experience in my life that related to conducting myself the way I am, to give you a sense of confidence yourself. Now, this is not a bad time to tell you about how the method of projection works. Just thinking about the well-known kinds, a Mercator is a very simple thing. You have a cylinder of paper around a globe, and the cylinder of paper is tangent to the globe at the equator. And you have a globe, let's say transparent, and there are the outlines of the continents on it. And there are, on the globe, there are the latitudes and longitude lines. And we have it light at the exact center of the globe, and so the lines, whether it's a continent or the great circles, make lines on the paper, the shadow lines. So we see that the light coming from the center, that where the cylinder is tangent to the globe, things are very absolutely correct. So the Mercator is exactly correct along the equator. Then, as you get further and further north, the angles get wider and wider, and finally, the cylinder of paper gets where the light at the center, no matter how far, it will never get to the edge of the cylinder, because the axis of the Earth and the cylinder are parallel. So there's a hole in the top where you never will be able to get any shadow projected. So the further north you get with the Mercator, the more and more distorted things are. So all the Mercators are actually fudged at the top. They deliberately pull down the data that they know about and just change the pace. Then we have something called polyconic, and the polyconic is as what most of the important charting can be done, where you can have, instead of a cylinder, you have a cone. And the cone could just touch the Earth at one point, so where it touched would be accurate, and again, as you go away from it's inaccurate. But the polyconic, we have a cone of paper that goes into the Earth and comes out of the Earth again. Can you see? You see it where there's a cone coming like this, and it penetrates here, making a lesser circle, and then it comes out into another circle. Can you see that? So where the two circles occur, they both are accurate, and so the intervening space is less distorted. So polyconic has been by far the least distorted of all the methods of projection in the past. Then there's where you have the light of the center, and this is sitting on a piece of paper. You have what you call a polar azimuthal, and so you might get a circular mapping, very accurate at the point of contact, but gets more and more distorted as you go further and further away. The azimuths are very much so. There are other modifications of what I'm saying. Those are the main classes. Now, common to all of those, wherever the sphere touched the sheet of paper, everything was accurate, and as you went away from the point of contact or line of contact, it increased in error quite rapidly. What I did was to take the globe with spherical icosahedron. I use icosahedron because it has the largest number of identical triangles. Remember that as we get a smaller and smaller triangle, the sums of the angles gets less and less. If I'm going to want to have something out in the flat, then I'd like to get as near to the flat condition as possible, so that there are 20 identical equilateral triangles in our icos, and that's the largest number of absolutely similar forms. Then we saw, yes, you can divide that into 120 small right triangles. The amount that the sums of the angles of a spherical triangle add up to over 360 degrees is called spherical excess. When the surveyors are surveying, they always watch out for the spherical excess. So I'd like to have the minimum spherical excess. For instance, if I were to use the spherical tetrahedron, its corner angles would be 120 degrees each. So I'd have 120 degrees spherical excess in my triangle. Right? 120, yeah. So if I use the spherical octahedron in the next system, I'd have 90, 99, 270 above 180, so I'd have 90 degrees spherical excess. Getting down to the spherical icosahedron, each of the corners is 73 degrees and 26 minutes. So I have when you have the 5 come together around one, you divide 360 by 5, and you come out 720. It's an equilateral triangle, so 720 goes to 60 each corner, 72 at each corner. A spherical triangle, icosahedron, has 72 degrees at each corner. So that when you flatten it into an equilateral triangle, each corner is 60, so that there's only 12 degrees spherical excess at each corner, and a total of 36 degrees for the whole total triangle. In other words, it is the one that has the least spherical excess to start off with. So I said, that's an optimum condition. I'm going to have to end it beautiful, because it is the excess divided 3 ways, which is symmetry. So what will happen is that, because I have 20 of those triangles within the 3 corners each, so there's 60 packages of 12 degrees each around the map that will subside to 60. And that is really an invisible map, because the total triangle, as it subsides, will simply contract. So it means that everything shrinks symmetrically. So just the interior of the triangle shrinks a little faster than the edge. The edge, absolutely no change at all. Because where the edge is, it's true contact. So I have by far the most, with those 30 edges of 63 degrees, 26 minutes each. You're going to get 30 times 63 degrees, 30 times 60. You have, all this is absolutely true. As I have by far the most great circling, that's absolutely true to start off with, and I'm going to have symmetrical subsidence locally. And the beautiful thing about it would be that where this contact, this triangle itself, that is all true. So all the change is internal rather than external. Now when you make 2 circles, one of a circular radius 1 and a circular radius 2, you find that you dismiss your error outwardly into circular radius 2. The area of circular radius 2 is 3 times the area of circular radius 1, so that if I dismiss my error outwardly, I have three times as much error as if I dismiss it inwardly. So that there's no way you can get a better condition on spherical excess than on the icosahedron. I could get down to smaller triangles because I could get in my 120, but I... Thank you, dear. I'm back holding my Africa. South America is one that usually tends to look kind of bad. It just don't find anything wrong with it. These are for the same to do, and so it really gives you very reliable information, and you can feel very confident when you see it out in the flat and know that you make these different arrangements. Just thinking about conditioned reflexes of human beings, I spoke at Haverford University 2 years before we published the world map, and I had all the pieces with me, and the mathematics department asked me to show my method projection, and I did. And he asked me if I'd come home to tea at his house with him, bring the pieces with me, and he had some children, his children, and he wanted the children to play with the map, see what they would do with it, the pieces on the floor. And they began to realize how to put the edges together so it would work. And he said, "Darling, you have the world upside down." And of course there's no up and down in the universe, and the mathematics department man was showing how ignorant he was, and the children were absolutely comfortable because there isn't any up and down in the world. Just how you want to look at it. But the kids had this freedom. I want to just stress this wasn't a matter of the children being ignorant, but that how quickly the reflexes can be misconditioned. If people are a PhD, extraordinary man. Now I'd like to go into watching our time. I think it is time to have a break, and then I'm going to get into some more of the mathematics. That'll end the map for the moment. Are we still on? If we are, I would like to carry on for just a second. There's a couple more things to tell you about that method projection. I'd like you to feel this with me and construct a little model with me in your mind's eye. I'm going to take a steel band, and it's nice evenly, you'd call it a ruler, steel ruler, and you can have inches or whatever you want. But a steel band, very nice and flexible one, rather thin, and clearly marked off in these basic increments. And then I'm going to take 3 such steel bands. I'm putting a hole in the end of the steel band And we're going to put a liner rivet in there that has a stovepipe through it, so it makes sort of a journal. I'm going to put a rod, two rods. There's a rod through this end of the steel ruler and rod through the other. These are very powerful, strong rods. They don't bend. I'm going to take then these rods are exactly perpendicular to the ends of the steel ruler. I'm going to have them protrude clear through down deeply, and I'm going to take hold of the ends of those rods and bring them together. And you're going to find that it makes the steel band very beautifully, and the rods come to a common center here. So it makes kind of a circular triangle, radius, arc, radius. Now I'm going to take 3 such bands, and I'm going to, where they make a triangle with them, and bring the corners together, then again having a swiveling rivet go through the hole of the corners, and these powerful rods can come through. We've got 3 rods at 3 corners, and the thing is standing up with a flat triangle like that, these 3 legs down. I take hold of the bottom of those legs, which are stiff, and bring them together. As I do so, we found that any 2 of them coming together made the single band bend, didn't it? So all 3 bands have to bend, because there's 3 rods, each one, any pair of them at the ends of any one steel band. So as I pull them together, all 3 steel bands bend. And as I do so, the farthest, any one side of the triangle with the band rotates away from the opposite angle, due to the rods also being brought to a common center, because they come to the center of gravity. So you can see that it makes each one of these arcs bend outwardly, which they're able to do, rotating away from each other. We then really get that's what that spherical triangle was that I had. I simply took those rods, the powerful rods, and brought them to a common universal joint, and we were able then, the bands in this case were a delicate, very powerful aluminum, high oil 73 ST aluminum. So you could go, that really was a sphere showing itself here, and as the rods went northerly and southerly, it kept just embracing the earth. The spherical triangles just opening a little further, closing a little further. I want you to understand then how then you're able to take a band of even module, absolute module, and make it into the spherical. I want you to understand this just to get your own confidence that the edges of the triangles, which are done that way, are exactly that way. It would be possible to take a light at the center of the sphere and project through a spherical icosahedron. But if you did, to a planet paper outside, you'd find as it went through the arc to plane, the angles begin to open up, so that it's not uniform module scale, uniform boundary scale. This is absolutely uniform boundary scale. And it's the only projection in history where you don't break open your package. In the Mercator, you're breaking open the top. You always have something open-ended. You have a line or 2 reference, and the triangle ends. But in this one, the line of 2 reference is continuous as a triangle, never breaks open, always contains and brings about the symmetry. I want you to really feel quite confident, comfortable about what goes on here. So this really amounts to it's a really topological transformation and not a shadow graph. So the words projection would have to be a mathematical projection, but not a shadow graph. It's a true projection, all right, but it is mathematical transformation and not a shadowgram. Now I'm ready to break, sir.
Okay, we're out of it.
Again, in the techniques of our medium that we're dealing in the video scope, and I have a great supply of slides that you know. One of the things we learn is that the video frames picture frame is just a little smaller than the 35 millimeter slides, so that we have what I usually like to show vertically may have to be shown horizontally. And I'm going to review really quite quickly those great circles that I had of maybe the pumping of the great circles. Instead of it being vertical like that coming down, it's going to be horizontal. So let me have the first slide. And in this, I think you'll enjoy it a little more. It's a good idea to get this feeling about spherical trigonometry. You can see the triangle up at the top, mounted out horizontally this time. That's we're dealing about a 72-degree angle up there. Next picture. And here we're down to 120-degree angles. Next picture. Now we're at 180-degree angles. Next picture. Now we're going to the negative spherical trigger, down in the southern hemisphere, down to about 90 degrees. But you really feel that transformation of how a triangle can rotate this way and change its. So we've had absolutely uniform boundary scale the whole time, and just simply change the angle. The angle is variable. Remember when we were talking about the necklace structure, and I was getting into structures, we found that the struts didn't change, only the angles changed. And so I look for what are the varying things. You begin to get a feeling very strongly about angles. In fact, I've discovered that you can describe all designing can be done with just two phenomena, one called angle and the other frequency. I'm going to have an axis of reference. So in relation to axis of reference, as I said, with a vector, I'm going to go off deliberately the start of this angle. I'm going to go off like that. And now I say it's angled, so I may not go off in the plane. I can say my angle goes this. But the point is, I'm going to go for so many frequencies. For so many frequencies this way, then change my angle, so many frequencies, another change the angle. So all you do is change the angle and frequency. And then you finally can outline, shape anything you want. I think that might be said. Otherwise, you said, I understand angle all right, but you say measurement. You go so far, but I use the word frequency for measurement. Now, next picture, please. I'm going to go through more and more of my slides. Here, again, we're showing something horizontal. Up at the top, you see three possible structures: the tetrahedron, 3 triangles around each corner; octahedron, 4 triangles around each corner; icosahedron, 5 triangles around each corner. And at the bottom of that array, you will see a tetrahedron, and it's about by my shoulder here. And then it's not really very well done. We have a series of the corners, 3 triangles coming together. Then it goes 4 triangles coming together, then 5, then it goes 6, and it's a plane. You can see there's a plane. That's why it can't be part of a system, because it doesn't come back in itself. And then the next one goes to -5, then -4, then -3. So there's just a same going between the northern and southern hemisphere idea. Next picture, please. Now, here if we can sharpen this up all you can to see. I have here an array, and I want to look into something on what would be the left-hand column as you're looking at it. Up at the top there's 1 ball, and then below it there'll be 2 balls, and then there's 3 balls and 4 balls. What I'm studying here are relationships between numbers of unique events. And up at the top, 1 ball doesn't have any communication to communicate to anybody. It takes 2 balls to have communication or relationship. Like I said, there's no otherness, no me. My awareness really begins with otherness, because it must be some relationship. So if I have 2 balls, I want to have, what are we going to say, how many private telephones we have to have to talk between, there's A and B. You need only 1 private telephone, because there's just A and B. So two people have 1 telephone. Now I'm going to have 3 people. So there's A, B, and C. So I'm going to have a telephone AB, AC, and BC. You're going to have 3 telephones. Have all. So at any in our telephone system, any 2 people must have an absolute private wire. So now I'm going to have 4 people, A, B, C, and D. I'm going to have, and what you're looking at up on the left-hand column there are the telephone wires between little points, and so between A, B, and C, A, B, C, D, I'm going to have AB, AC, AD. That's 3 of them. Then I have to have BC and BD. That's 5. And then I have to have CD. It takes 6. 4 people have to have 6 private wires. This is our friend tetrahedron, which has to have 6 edges. The 4 requires 6 connectors. So, in fact, you find this gets to be a sort of fundamental model that way. You find then the next, there are 2 columns I have up there. One is then the actual number of telephone wires you have, and then we put up the number, because if the first case we found we needed none, then we start with 1 between 2, 3 require 3, 4 required 6, and 5 required. Now I'll tell you it is n to the 2nd power minus n over 2, because you find it, you actually learn the equation. N to the 2nd power minus n over 2. So I have 5. N is 5. So n to the 2nd power is 25 minus 5 is 20. So divide by 2 is 10. You're going to find have 10. So the numbers are going like 1, 3, 6, 10. Now the next one would be 6. So 6 to the 2nd power is 36 minus 6 is 30. Divided by 2 is 15. It would be nice if we could have the chart really.
Because it can't get much clearer than it is, and you could probably see it better if it was drawn.
Oh.
But do it your way.
You're going to introduce this later then, or what?
If you wanted to just draw it, the connections on the board, you could see.
I see. I think you're getting it in your own perfectly clearly. So I have a series of columns back. If I could go back to the drawing itself. The first one was all the people in the telephone wires. Then the next was a summary of how many telephones are needed. Is a vertical line of columns. Now I find that those numbers 1, 3, 6, 10, 15 are actually the total number of balls in a triangular collection. Just have 1 ball, then 3 balls. Then you get 6 balls in the next triangular collection. 1, 2, 3. Remember, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The next one is 15. So we find that the numbers of relationships are triangular numbers, they're called. That gets to be very interesting. Then you find that those triangular numbers are fascinating because if I take 3 balls, for instance, and I sit them on what the next is 6, 3 plus 6 equals 9. Or if I took the 6 and had to sit on the 10, I get 16. Or if I took the 10 and put it on the 15, I get 25. What do you get? 9, 16, 25. These are 2nd powers. There's any two sets make what we call the 2nd power. I don't use the word square anymore, you notice. I always say 2nd power, 3rd power, 4th power. I never get caught with saying squaring and cubing. So we find then that here's a triangle sitting on top. A triangle always 1 ball less, sitting on top of one, that makes the 2nd power number. You'll find that you take that top one and hinge it over, it lays over, it makes a diamond. And when you look at that as a diamond, may I have the picture itself back here, because we have these pictures of the diamond then. You'll see they're stacked up there, and then we get into the diamonds where a diamond simply is a square, but remember, these nest at 60-degree angles instead of 90. So it's a diamond. And you can count up them. You can understand it's the second power to see how the second half completes how the 6 completes the 10. Now, then we find that if I stack these layers, 2 layers together, and then I get tetrahedra vertically. So I find that whereas you and I need a private telephone, or any two of us want that private telephone, I have that in there. I could also then call those the relationships between our experiences. You're a child and have an experience and have another experience. So what's the relationship to it? If you understand, you begin to understand the relationship between the experiences. So then I find that if I stack my relationship with all my experiences together, in the end comes out a tetrahedron of such and such a frequency. In other words, the numbers of the telephone were triangular numbers, and the sums of all, and of which there's numbers of telephones, and there's the numbers of experience I've had in my life. These are all the relationships between all the experience I've had in my life. These are all the understandings I have of all the experience I've had in my life. There's understanding relationship to those points. That's what those triangular numbers are, the understandings to a relationship. So then those are individual experiences. Now, I keep integrating this set of understandings with a new one. I've just had a new experience. So the final tetrahedral stack up there is a sum of all the relationships between all the experiences you have. Really understand being a comprehensivist in the way I carry on with you is very much relating then to all those relationships. So I'm really carrying on in a very tetrahedral manner as far as that it comes out in this elegant, beautiful tetrahedron. Just one more, whatever it is, always comes out a whole rational tetrahedral form, or a whole triangular form. I find this very exciting. What I call this then the underlying orderliness in superficial disorder, where the experiences seem to you and I very disorderly and random, but suddenly find the whole thing, absolute order. You can't become disorderly. It becomes really very exciting matter. Now, how the next picture then? I told you earlier about the 2 general dynamics scientists who are making experiments with titanium sheet. They're making experiments with titanium relative to re-entry problems in the rocketry. Remember that? I had 2 hemispheres, one half an inch less in radius than the other, and that they were concentrically arranged, and then they were actually sealed up, welded up at the bottom, and so there's a space between each one of them, a half inch. And then they clamped it into a frame, and this is what you're looking at in the picture, and the atmosphere is able to come in underneath the frame into the inside the dome. So the atmospheric pressure pushes the inner dome outwardly like that, as it has very normally. But then they exhaust with the vacuum pump they have between the two, so the atmosphere operating in the outside one pushes it in towards the other one, and it dimples in. I spoke about dimpling, and dimples in the exact icosahedral. This happens to be it turns into be a 4-frequency geodesic tensegrity structure. In other words, I had also been giving you the way the molecules of gases operate and so forth, and this is I'd say they want to get the most economical, which means always a great circle. So they insist not on lesser circles, to get beautifully into the whole great circles. And when 2 great circles, remember, Cross did this, but 3 great circles, triangle. And now there's all this triangulation in there, and an enormous number of actions, so they average out an equilateral. They keep trying to get absolute equilateral. So the whole thing just makes itself get orderly. Time and again I get so excited and find how beautiful life is really carrying on, how the universe, under all these things going on around us, but there is this lovely order. Next picture. It's fun to see what's going to come up here. Now, we see 3 lines crossing one another. Now, one of the great differences between myself and the mathematicians is that all the mathematicians assume you can have a plurality of lines go through the same point at the same time. if you get in geometry where they get into the non-Euclidean geometry, get hyperbolic, or you're assuming still plurality lines going to the same point at the same time. This is exactly what physics finds can't happen. Because I said a line has to be in action. They have the lines going to the same point at the same time as a point. And I simply say to you that the lines then, if one could go through it, and then another, if you have a machine gun and a bullet's coming like that, you could have another machine gun and synchronize them so one went through then the other. And it might look like a couple of lines crossing, but they're not. So may I have the next, hold the picture a minute. I want you to notice then how those three lines are really crossing. And what they do, one has to be superposed on the other. So they just automatically do what's going on here. May I have the next picture, please? And this next picture, you see what the physicist is doing. The difference between the mathematician and the physicist is that we find that when two events, because a line is an event, there's just no question about it. You can't have it with, just imagine how I proved that to you yesterday. So we have an event, and there's already an action taking place. Therefore, that's what we call an interference. And with an interference, it could be a glancing blow, and be what you call then a refraction. Just still ticking here, and it changes angle though. That brings about refraction of light. That's exactly that. There can be a very tight blow like that. I have the picture back and again, oh, I see. We get then a bounce off. Then there could be another one where they go in first through, and then there's a fourth one where we have a smash up. Now these are all the things that go on in the cloud chamber when the physicist is bombarding, sending a neutron or whatever maybe. You can certainly see these bouncings around, and they are all to do then refracting, reflecting, smashing, or the one-fourth one have where they're going almost the same direction. They get what they call critical proximity, and they get one of those mass attractions. They become one. If the angles of convergence are close enough, then you really can see that mass attraction taking over and then pull over. We had a very interesting experience in the Navy in World War I. I told you I was in a transport service where we took these 130 men over. With the German submarines and enormous houses, they tried running at night without lights. Of course they didn't want any lights, because the submarine watched for and laying off there, watching the silhouetting against those lights and so forth. So lights are anathema, so they didn't want any lights. So these enormous groups of ships were going together, and they had to want to stay together. Enormous danger of following the other man at night. It was a torturous kind of a game. On one occasion, two of the big transports found, just in avoiding trouble, the end of one got overlapping the other like that's pretty close. There were two big ships, the Mount Vernon and the George Washington, both big ships up in the 30 or 40,000 tons, big. And they got where, being in the water and being big ships, their mass was enough so they began to attract one another. That's when you get big ships at sea, they really begin to show that mass attraction that you don't see of two apples sitting on the table. The pull of gravity is so great, there's friction of the apple on the table, they don't try to go towards each other. But these two ships are free at sea, and the acceleration on there found them being pulled together. And if they'd ever gotten, the seas were heavy, they would just shoot each other up and lost. I think involved on that particular case there were they would have lost about 20,000 human beings. The captains of these two ships tried to see what they could do, because the mass attraction, if you try to get too fast, the bow would come over and so forth. They tried to figure out how to, if one could accelerate a little faster than the other, and they made troubles. They finally found all they could possibly do was to open up an angle between them and just keep them apart. The idea that finally could pull apart to get out of that critical proximity to the second power business. They finally did, but they were actually a whole day pulling apart. So when I spoke about lines coming together, one, you can have then light refraction. One, you could have reflection, real bounce off. You could have a smash up, or you could have angular convergence, be so delicate that you have critical proximity and a possible fall-in. Those are all the things that happen in the cloud chamber. This is all the physicist deals in. And this is exactly where the mathematician completely lost. He's lost all the privilege of things because he said the lines are going through the same point at the same time. This is typical, again, of what these false assumptions that superficially said it's obvious. They said two lines go through a point. Anybody see that? Two chalk lines on the blackboard. But the actual fact, if I do it on the board, chalk or whatever it may be, you look at it here. You really see it literally cross exactly like two. Let's go in the snow, and you have this tie go this way. The next one is the top one. It quite clearly is absolutely separate. It always is. So being completely experiential, completely operational, these are the kind of very exciting informations we get. So now we're playing a geometry where we don't get deceived. And this is very, very important. We're dealing with all those because there's a vectors always. My geometry is vectorial. Now this brings me then to explaining to you a little about my grand strategy when I was young, saying I don't think that nature has a department of physics, mathematics. I said that to biology, and has to have department head meetings to know what to do when a leaf drops in water. I said I think she has only one department. I would like, if I can, to find what it is, because the chemistry of it says it's very simple. It says H2O. That's the way it associates, and it's very beautiful low numbers. So if I'm going to do my geometry, and I didn't like, I said, the geometry where the teacher said this is a ghost cube, and it didn't have any longevity, it didn't have any heat, it didn't have any weight. I want to get those qualities in. Now, I'm not the first one to want to do that. The scientists going really back to Babylon are trying very hard to do that when they chose the 60 minutes and 60 seconds as a fraction, hoping they'll be able to correlate it with the circle and so forth for trigonometry. And we have then the scientists having x, y, z coordinates, and then they needed to have those qualities of mass, so they couldn't find really anything, so they very arbitrarily getting into the centimeter. It's nice, it is okay in relation to decimal system, if decimal system is what nature is using, but the arbitrary thing is decimal because we got 5 fingers in each hand. So the insistence is going to be decimal. So we have the centimeter, one cubic centimeter, and it is really a cubic centimeter with water, they said. Now we have this what we call a gram, and we know what the weight of that water is then the basis of weight in relation to volume. We want to have weight and volume coming together. Then they found that the water changed its volume with temperature. And so that became very upsetting. So finally had to have at 4 degrees centigrade, it's a temperature there, and then it fills one cubic centimeter. That gave you then the official gram. So we have, I spoke about dealing in weight, lifting a given weight against gravity, a given distance. So lifting 1 gram, 1 centimeter in 1 second. CGS, this is centimeter gram second. And in relation to X, Y, Z coordination, these became the buildings. But there was no time, even then they didn't have time in there. So the longevity didn't say how old the water was. There was nothing in there to really identify time. So I became interested, and I said, nature does have a time, so I find that you're just so old, and I'm so old, and etc. There is a time dimension. I'd like to have that in there. So here's the way my own strategy began. You might as well just know, because this goes really way, way back. So in physics, mathematics, and in my preparatory school for Harvard, I became very interested in, for instance, in the fact that Avogadro, I like vectors. I said if I used a vector, because a vector is an experience, and does represent an event, and it does represent the amount of physical universe as mass is going in a given direction at a given velocity. Because velocity then has time in it. So this is very satisfactory. So I got both frequency and time, all these things nicely in there, and those kind of vectorialized are beautiful. They don't go to infinity. Again, the mathematicians keep telling me about infinity. I remember when the teacher said this line goes on to infinity, and I said, "Have you ever been there?" I said, "How do you know it goes to infinity then?" So I said, "Where's the other end go to?" She said, "Infinity." I said, "Which way is infinity, dear?" And so she couldn't tell me which way infinity was, and I didn't like this infinity very much. So I liked something, because I personally also never experienced infinity, and I'd like to have something along my experience. So I like vectors because they're absolutely discrete length of line. They don't have inherent extension. It's just exactly what you see there. So I wonder if I can't get up a geometry out of vectors, because that would have then the time quality, and it would have the velocity, and the velocity and mass impact converted to heat, so it had all the elements of experience were in it. So if I could only get a geometry of vectors, that would be great. Then came the moment in my learning about science, learning about Avogadro. And Avogadro had a very extraordinary intuitive awareness. I spoke to you earlier about the human beings and the 5 lights in the sky and coming interested in it. I also spoke to you about Priestley making his experiment with fire under bell jar, and how Lavoisier identified, he said, why the products of the fire added up to more than the weight of the things he put in was because something else had joined, and it came out of the nothingness, which was the air. Out of this we then got, for the first time, we got elements were gases. And this was so terribly important as to really open up, as said, thermodynamics and everything. It's not surprising that the next 5 elements to be discovered are all gases, and it's because we have the enormous competition who's going to run the ocean world. So the French are putting up money for their scientists, and the king of France and the kings of Spain, everybody's putting up money for their scientists. And so that we have Rossi is the French. Incidentally, one of the most extraordinary things that society ever did that was blind and short-sighted was realized it was the very essence of understanding really the steam. Therefore, English, who did want all the great pirates at headquarters in England, very eager, so they're putting up money for. So Cavendish, the next 5 chemical elements found are all gases, all Cavendish. Now we have enormous preoccupation with these gases, and Boyle and others, and amongst them with Italian scientist Avogadro. And Avogadro, very astutely looking at all, comprehensively, not to being too specialized, looking at the total idea of total gases. As his patrons came and said, "I want you to catch up with these better have better steamships than these other boys ever did." Avogadro then said, "It looks as though," and he hypothesized, "that all gases under identical pressure and heat would disclose the same number of molecules per given volume." Boy, I said, this is something. He then went on to prove it. Suddenly we have then volume and number common for a plurality of gases, which are elements. Now, here I had a place where elements, which are elements because they are unique, were coming together volumetrically and number-wise, which is very much better than just putting water into a cube. Nice. So I said, it could be because elements go through their liquid, their gaseous, and their crystalline states. There seem to be that kind of intertransformability. And the only reason certain things are crystalline in our present is that it's relative conditions of this part of the universe. But it has to be this set of heats. If they were in the sun, they're going to be incandescent. They may be plasmic. So I see then, because the elements can go through liquid, gaseous, then we might think about all of the elements under some identical condition. So instead of just saying under identical conditions of heat or pressure, that's what he had said about the the molecules of gas. I said, it could be. You could generalize that, and I said, all elements under identical energy conditions, which means either heat or pressure or any of them, under identical energy, might disclose the same number of something per given volume. I don't know which one is going to show up. I thought that should be more or less the nature of a generalization. So I said, if then I want to have a geometry made of vectors, and all the energy conditions are the same, all the vectors will be the same. That's wonderful. So I said, means that all of them be not on the same length, they all be converging the same kind of angles. I said, can you make a model where all the vectors are the same length and they're all converging, and also, but they have to take care of the actions, reactions, and resultants, so there must be angles, joining angles at both ends of the lines. Can I get a system where all the vectors are in a closed system, all the same length, and all the angles are the same? Now that turned out to be exactly what you're looking at up here. Again, a very fortunate thing happened in my life. Often what seemed to be misfortune turns out to be fortune. I find that life is highly compensatory, because I was very, very short-sighted when I was born. And so short-sighted that, so very far-sighted, that I can't, when my eyes, the glasses off, I see exactly now what I saw when I was 4 years of age. The correction has not been changed at all in all those years. This is my 76th year of these lenses. I see absolute blur of faces. I cannot see human eyes. I can actually make out some darkness where eyes are, and I can see more or less a shadow of nose. I can see the two sort of dark colors. It's purely color matter. Nothing matter with my spectrum of color. So there's a pinkness. This side of your face is a little lighter than that side of the face, and I get really just a real shadowiness that are the eyes. Very like Marina Lawrencean kind of a painting. And there is a little bit more of a pinkness in here, and I could make out little color differentials. So I did see a human eye until I was 4 years of age, 4.5 years of age, and I had my glasses. Now, because of that, I tended to try to get my. I didn't know how a little child knows. What I see is not what everybody else sees, so I assumed everybody's seeing the same way. But my problem of understanding was really quite a different one from the people who could see the details. And I had a sister, 3 years old, and I wasn't. She was always continually telling me the things she could see. And I thought she was making it up, so I didn't want. Every child has imagination, so I thought I had been read fairy stories. There's fairy stories. I'd invent what I could see, and I could see some very extraordinary things. And I would always get laughs, and my sister didn't seem to get any laughs for her description of what she could see. So you imagine what happened when I was suddenly 4 years of age, and I saw that she hadn't been telling me stories at all. And I suddenly saw hairs. Now, I spoke that there's a compensation here. I went to kindergarten and before I got my glasses. And in the kindergarten, the teacher had some dried peas, semi-dried peas, and she had toothpicks. And she told us to make structures, to stick the end of the pea in here, and the toothpick in the pea, and we found they joined the toothpicks so that make structure. All the other kids who could see, the minute they were told to make a structure, immediately tried to imitate houses. The first thing they thought of. So they were all rectilinear. Now what I did, because I couldn't see at all, I wanted to feel something that feels good, so that a square, those forms didn't feel right, but when I got to a triangle, it felt great. So I felt I could really feel that as nice and stable. So I've made literally a structure like that. And I remember the teacher calling other teachers from the other school there to come over and look at it, and they were all very surprised at why I made this strange thing. But purely a consequence of my not being able to see. But I was not trying to imitate something. She said make structure, and I got to it felt right. You can understand that as somebody going around groping the way. It's a purely matter of feeling. And anybody working in clay would just have that kind of feeling, whether it's going to tip over or not, whether it's cohering. Anyway, I did do that. So it was something deep in me also about that. So when we have the moment of my being saved by Avogadro, he seemed to be giving me some universal condition, and I wanted to be used vectors, and I felt this thing. I said, I think I can make that, so I made this. Now, this is called in mathematics an isotropic vector matrix. Isotropic, everywhere the same. Isotropic vector matrix. So I found I could make it an isotropic vector matrix. That was just great. But then the isotropic vector matrix turned out to be simply spheres in closest packing. Remember, the me and the otherness, and then we suddenly come together here, and then suddenly we roll around on each other. These little balls are really great. The styrofoam wants to play to get the feeling of that rolling around. From where I am, in fact, I'm rolling, you don't really notice that. The profile stayed just the same. And so then I get the three of them rolling together, and I get the one on top nesting in it before. And there's your 6 vectors, and so spheres in closest packing, all the same radius, unit radius spheres, closest packing, they simply automatically come out the isotropic vector matrix. Now, we were interested in atoms and how the atoms behave, and the volumes, numbers per volume and all those things. It seemed every kind of way this is very satisfactory matter. It was at that point that I also then said, I'd like to see about a nucleus. That's what brought me then into finding then the 12, 6 around 1 and a plane, and 3 on top and 3 on the bottom, giving us then the vector equilibrium. We got a lot of these balls, and I really would like you to do some experiments with them yourself, because I don't want to slow picture down too much here. And you're all getting pretty well versed here. Now, I've also given you tetrahedron, and I've also given you the idea of Euler's topology, that vertexes and the numbers of the edges are not the same as the vertex. Remember that for every vertex we're going to have 3 edges and 2 faces. That's an absolute relative constant abundance of those in the universe, in addition to the polarity 2-ness, which has to be taken care of. And that was what was not recognized by the topologists. They didn't realize there was a hierarchy. It was never understood there really was this hierarchy I'm finding. Completed my own discovery to come then where the tetrahedron was unity, which you can see how absolutely logical it was. It was a minimum omnitriangulated vectorial model, and a cube just didn't work. It was very uncomfortable. So you can see how quickly I really got into, sort of spontaneously, into, I want to see how, but this is where a child carries on. I'm saying, of all the things that I find important, I don't think anything is quite so important as naivety. Just cherish your naivety. Don't let anybody try to belittle you because they say you're naive. This is the most beautiful thing we have. So I think that I was very naive many times, as a sort of off character, seeing the wrong way at first with the teacher and everything, and then I didn't. With my big glasses, I was kind of ugly-looking character anyway, and never was a teacher's favorite. I'll show you. In fact, often my friends discovered that to such an extent they found that they could play tricks, and I'd be the one to get the blame. It was sort of a standard matter in every class I was in. I was continually having to stay after school and so forth, and when they stay after school, then the teacher was rather nice and got saying, "You really like mathematics very much, and I'll teach you some more." Actually, at Milton Academy, where I was, the mathematics teacher said, I think you might just well go on to in the college mathematics, and so I went through a whole lot of mathematics when I was still in school. So simply, this afternoon time when I was being penned in there anyway, so it came out fine. There are compensations that go on, and the kids didn't know what favor they were doing me. I didn't know what either. I don't want you to at any time think that I'm being something abnormal or smart here. everything that's happened in my life here so far, as far as I can see it, comes really out of the circumstances, the physical circumstances. And this, of all the things, I think is being able to see properly, nothing was quite so important. Because at 4½, imagine if you've never seen a hair, you suddenly saw a hair. And you've never seen a dewdrop before. Can you imagine? I hadn't seen eyes. Particularly eyes of creatures, eyes of those kittens and eyes of the snake. And these eyes, I seem to be able to talk with people with eyes. I just love snakes and toads, and they like me, and we get on and fill my blouse up with them. The people holler about that. But I want you to understand, I don't think anything went on here with me that wasn't just a very fantastically normal, average character with certain physical deficiencies at the outset which get fixed up. Because at 4½, I really started life all again. Imagine you get a second chance. I'm sure that through the years, when things went badly, I'd say, because I couldn't see at first, but I would say, when I don't see and don't understand what's going on here, I think that all I got to do is to wait a little. There must be something in me very psychologically that came about through that delay and a second sight, a second take, where you really suddenly understood. I think this has helped me to hold on many times to the total package. And certainly that business of not being able to see details, I was having to put together smelling and hearing and touching, which were very much less effective than the seeing. So I was using a three-way system to sort of zero in. And so I personally, my grandson said, I'm not sure that I'm really being effective with human beings when I say this, but I'm confident the only thing that is important about this particular character, me, is that I do represent an average character, more or less getting peeled off by something wrong, like the kid's fooling you, so you get peeled off the afternoon. I've found myself getting isolated more and more, but to give me more and more perspective on the show, and tending then to see long distance, to put together big patterns. When I say then, as far as I'm concerned, I am very clearly a demonstration of what any human being can do if they're disembarrassed of a game where society is trying to make you specialist, trying to, and no question about society doing what it did in great love. The grown-ups really feeling enormous affection. They're sure they're doing the right thing for their kids. There's anything but malevolence in here. So I don't think, again, you can see anything if you assume the bad or good in here. You have to really understand how people got caught in the picture they're in, why people do, but that's all to do. And you may find out something. Now, I have some more slides I'd like to go on. Something I'd like to show you here, because I found there are 5 of these balls, and 5 sets of the tetrahedron have been put together. Remember how when we had a tetrahedron, let's look at it, the corner, tetrahedron in the corner, you get 4 tetrahedra and 1 octahedron in the center. Remember that? That's getting clearer and clearer to you. But I also pointed out to you that vertices and edges are not the same. So sometimes you're looking at tetrahedra and they look like this, and when you're doing that, these are entirely vertices. The spheres are little points enlarged. This is a vertexio, topologically. And then when I see it, that's a line, then I can make it out of solids, because those are areas. There really are, these are 3 different topological phenomena. The counts come out differently. It's very important to realize that, because then we've got 2 balls here, but there's only 1 edge between them. That's one reason why we came out where 4 balls had 6 interrelationships. They're not the same number. So I want to show you how, what you're very familiar with now, putting a tetrahedron, 4 tetrahedron in each corner, and 1 on top. So here's a tetrahedron. Another tetrahedron here. Another tetrahedron sits here. Now, according to the way we've learned it in areas where it looks like solids. Then you put a tetrahedron on top and you put an octahedron inside here. That's not what you do at all. You say an octahedron, I'm going to take a tetrahedron, turn it upside down. excuse me. This tetrahedron, I'm going to let it in upside down, and each of these four are going to come in the middle of those. There it is. Sits right down there. Now I'm going to take one more, and it sits right on top there. Now we got a 3-ball or a 2-frequency tetrahedron made out of 5 tetrahedron. Here's our number 5 showing up quite interestingly, where you'd had an octahedral kind of 4. There's a prime number difference in there. So it's very, very important not to get fooled about. See, it's very neat. So vertexial associability comes out differently from edge sociability or face sociability. In fact, vertexial sociability was the, excuse me, dear, do you want to have me take it out? There you're 5 in a row. So, vertexial sociability is universal joint. This is where the gases are, remember? And edge sociability is liquids, still flexible, distributing lows, and face sociability is triple bond. This is single bond, double bond, triple bond. And then we get the greatest tension, but no flexibility, no distributing loads anymore. And this is crystalline, this is liquid, this is gaseous. This way where I suddenly found out how to integrate Willard Gibbs' phase rule dealing in the chemistries, the liquids, crystalline, gases, with the topology. So I found they're all the same. And that was, again, a breakthrough. There have been very many breakthroughs in my life that where said you don't understand. For instance, there's something I'm sure you've often heard of, the 4-color problem. Why do you need no more than 4 colors to do any mapping, so that you'll always have different colors between any two areas of a map, no matter what the shapes are? And this is simply because nature does work then in tetrahedra. And a system, a map is always going to be on the surface of a system. There's no plane all by itself, no interminable plane. It's always going to be a surface. And it's always going to turn out then that you've got a triangle, because you get down to triangles for the net structure, and the triangle on the outside of the sphere is the base of a tetrahedron whose center is the center of the sphere. and the tetrahedron is going to come about that way. So the tetrahedron has 4 colors. And the 4 colors, you have a red on the outside, there's a red, the blue, green, and yellow at the inside, blue, green, white on the side. You find then these act like gears, and every time you just have those 4 colors, and you have for one outside, you got 3 buried. So there's a universe of 3-way gearing. They just can't come out wrong. So you can really make a model. This then proves, for very many years, it's been said for really over a century, nobody ever proved the 4-color problem to show why. But this is fundamental, because you and I are dealing now fundamental to systems. I've been able to say absolute limit conditions all the way through. We're at the simplest, and here it is. Okay. I now would like to have the next picture. This is really quite a simple one. Well, I wanted you to remember I've talked about pulling. Could you eliminate me for a minute? You have on the left-hand side pushing, and we find then it's tending to be a sphere. This is a precessional effect. You push on the 2 ends, and the whole thing begins to go, increases in girth, and you pull on it, and it contracts. I just want you to feel that. Now, before we go on more pictures, I'm going to go through something that relates to a statement that we made here just a few minutes ago about, I just think about children and human beings apprehending So there is the touching and the smelling and the seeing and the hearing. And I'm sure that sometime we're going to learn about this electromagnetic, telepathic relationship, but the ones we know about are the touching, smelling, hearing, so far as seeing. And I find, as I grew up, the insurance companies had equal indemnity for the loss of a hand and the loss of an eye, for instance. There was a sort of, as I grew up, there was a sort of feeling, you're being told by grown-ups, you know, you may lose your hearing, but you got your sight. These are, they were sort of alternate faculties. That's the way they were looked at. They were not really evaluated very tightly. And I felt a very great necessity to make a experiential, operational assessment of our senses. Having been then myself not having had the seeing of the outset and having primarily the hearing and the smelling and the touching. Because as I was young, I can't tell you how much I smelled. The smelling was very, very, I really was almost like a dog. And I knew people by the smells. To such an extent, and my smelling said that just in the last few years, my sensitivity of smelling is going down like my hearing. It seemed to be nervous, the nerves are breaking down. But through my life, smelling has been so, I always really smelled people. First, the first thing about them, and if they smelt wrong to me, they were not going to be my kind of a pal, that's all. There was no question about the smelling. When they looked great, but didn't smell right, I just learned to turn away. You better get away now. There's going to just be trouble. So now I'm going to go into this assessment of our nerves. And I'd like to make a good experiment on a good scientific basis now. And I'm going to take my body and I'm going to bandage up my mouth and my nose. I'm going to give myself an oxygen tube so I won't be asphyxiated. And I'm not going to use it, so I just know that oxygen is very prominent in there, but that's not what I'm dealing in here. It's not going to give me information. I'm going to cover up my ears. I'm covering up my eyes, but all blindfolded. I have my body. I'm naked. And I need to get some information. And certainly, I'm not going to, in any unknown territory, I'm not going to step over here. I have no experience to tell me that I step there and keep my balance on this foot. I'm going to try it very, very much before I ever throw any real weight there. Just a kid testing ice. So I'm also going to be, I don't want something to run my head into things too, so I'm going to be doing this. So as I move along, I'm going to be being very, very tentative, and every way I'll be acting like an insect. And under these conditions, I find that I would also begin to get a little familiar with the floor, and I'll get to know it. I have a good angular sense, and I sort of feeling of orientation like this. If I turn like that, it's going to be like that. I can really feel what comes next here, because there really is a pivotal effect. You get to learn just exactly what it's like on your feet. I don't know whether you've ever done this as a child, but off in the country, if there's a place that you've just really enjoyed yourself tremendously, little kid, and they let you get out at night a little, and you find that there are paths, so you get so familiar, the feeling of the paths with your feet, that you can run down that path at night really quite fast, even though you can't see it. Foggy night, you still feel very, very comfortable with your feet. So I would say then, if you just had the touch, you'd gradually learn about a certain amount of territory. And it could be fairly large territory. And if you feel really comfortable, within that territory, you would dare run. But with just my legs, and as short as they are, I'm not going to cover very much of my planet Earth, that's obvious. The information that I would get, because I'm also going to be watching this run through the night, and I've learned that other things some fall in there once in a while, so you can't be too sure about the space which you're going to be doing this all as you're running along like that. So I see then that the limit of the information that I can reach just standing still, as I start off, is a limit between one toe of one foot and the finger of another. This is the total. This is considerably more than my height. I'm going to have a very tough, tall basketball player. I'm going to give him 10 feet stretch from his toe to his fingertip. Let's keep it a simple number. Somebody say then under the conditions of just touch, you have a static range of 10 feet. But under the, you and I can run possibly up to, say, like 5 miles an hour, and the amount of time that in a total lifetime, say all the days, about how much, you and I would have a dynamic thing where I could run, say, 5 miles an hour to get information, plus a static reach of 10 feet. So I'm going to put that on the board here. We got, on a tactile basis, I'm going to have a range, a static range and a dynamic range. The static range is going to be 10 feet, and this is going to be 5 miles an hour, 5 mph. A mile is about 5,000 feet. So if I divide 5,000 by 10 to get down to 500. Well, this is 1/500th. This is so I'm going to call it 1/500th of miles per hour. Because I want to get it in relative to miles. Now the next thing we have, I'm going to cover up all my skin so I can't get any information from my skin. So looking at running, I got information all over my body if something runs through. And I also felt heat. So now I'm going to cover my whole body, and I can't, because I would also, I would not come too close to fire. I'd feel that heat. I'd feel the cold this way. You get a lot of information, all right. So now I've covered up all my skin, and I can't move anymore. I'm not allowed to do that. And I open up my nostrils. My eyes are covered, my ears are covered. That's all I have. And what can I learn? We have learned that sailors, time and again in history, on sailing ships coming in from long sea voyages, have been able to smell citrus groves or pine at sea with no wind. It was calm, a mile offshore. You can smell pine and citrus a mile away. So I've got a static in this new one. This is now the olfactory, and I have in that a 1 mile static against the 1/500th, and you can smell without, that was 1 mile static, but if the wind is blowing, it could bring you a lot of smells. And how fast can the wind blow? Well, at Earth level, we have 400 miles an hour on some of the stratosphere, but the level of which you and I operate, fastest we have down the Antarctic, so 180 miles an hour. So that with 180 miles an hour, your smells can be brought to you, and often we get forest fires, information about them really considerable distance. But I've taken the static, the air's dispelled, they get thinner and thinner, so that the mile is as far as you get with the, so there is a dynamic additive to the smelling. So I'll give you 200 miles an hour dynamic added to the smelling. So I didn't really do this column very well. I'll leave this, these are all mph here anyway. So we had 1/500th and 5. This we have 1 mile static, but I'm going to give you 200 miles an hour in the dynamic. Now we're going to cover up your nose and all your skin and open your ears for the first time. Eyes are covered up. What do we know about this? We know that humans have heard the atomic bomb blast in the desert 100 miles away. That's not usual. If it's just you and I trying to shout to one another, we can hear explosion considerably further than we can shout to one another. So I have to use the explosion. And the atomic bomb blast is the biggest, so that we have to use, the static here is 100 miles an hour. This we're now dealing in hearing. And then your speed of sound in air is 700 miles an hour, but if the air is blowing your way, it makes it come 900 miles an hour. Actually makes it come blow. It can blow towards you or blow away from you, because it is in the air. So we have to have, there is then a dynamic additive, so this gets up to be 900 miles an hour. Now I cover up all those touch, smell, and hear, and open my eyes for the first time. And so I've been going in with you. Man, you can see a galaxy a million light years away. I find that the range is so incredibly large that if I try to put down what it is I'm saying, I'll have to take that's a good one, the 1 million light years away. So we take our million and we multiply it times 6.5 trillion miles per year. So 6.5 trillion, we have, so what do you have here? You have your 6 zeros in your 1 million, and your trillion you have 9 zeros. So you have 6.5 times 1, so 6.5 times 1, and you have 6 and 9. You've got 15 zeros, so you've got times 10 to the 15th power. This is the number of miles that you and I are seeing, 6.5 times 10 to the 15th power. And if we want to say it out, we'd have then, so it said 15 zeros, so let's put it down that way, 6. So we're saying this is millions, billions, trillions, quadrillions, sextillions. We're seeing us, we can say see a sextillion miles. So this is the sight. So it is an incredible figure. So we just simply have to write it 10 times 10 to the 15th power. It was 6 times that. Okay, then I've got that is a static range. Then to that I have to add that velocity. That was the actual numbers of miles or so. So the velocity which I see is then also then the 700 million miles an hour. That's my velocity. Now if I try to make a chart to plot these things, you find that these first three are really pretty close to one another. So I can get them on my chart all right, but for the fourth faculty, the seeing, I'm going to have to take an airplane and I'll be going quite a long while before I come to the point where I plot them. So I find that the first three senses are really very closely coordinated, and the seeing one is very remote from. So the fact that I had the first three at the beginning put me in really quite a very pedestrian kind of a way, and you imagine the excitation of receiving this one secondarily. But I think the kid's probably using the first one primarily and not really realizing what a jump up that is. So again, I think this is part of why circumstance happen to take a very average character, in fact, a fairly efficient average character, and get it into all this trouble. You find me continually then trying to find hierarchies of the experience, trying to get total experience all under one chart. This is my proclivity all the time. And now this tells me a lot more. When a child is born, I'm sure many of you, all of you, have been near a newborn child. That's your sisters or mothers or some friends. And the little child is lying there, and if you notice, his hands seem to move rather deftly. At first, they can move their heads and suckling and so forth, but their hands and these motions are sort of spasmodic, the legs, but the hands seem to close. You'll find yourself tempted, and I've taught so many people do it, because I know immediately I had a temptation to put my finger in the little child's hand, and sure enough it closed on it just as deft as could be. It's amazing. See, it feels as though this child is done talking through hand. I like to take my hand away, so immediately opens up. So I start to pull it away, opens right up, accommodates, bring it together, immediately couples up. Now, this ought not to surprise us because the child has been in tactile communication with its mother for months. It can't see, it can't hear, it can't smell in the womb, but it feels. So the tactile is there. So tactile is already operative when the child comes out, highly developed, it's a very sophisticated feeling. So it's considerably later that the next thing comes in outside of the womb is then the olfactory smelling for the udder and so we're going after milk. Then considerably later, the child begins to hear. And the very last thing it does is to see. We find then there is a hierarchy of relative magnitudes of effectiveness, but they are employed in that order. So the first one that is used is the tactile, second is the olfactory, the next is the hearing, and finally the seeing. This again, when you find such an agreement of hierarchies, of rates of use and so forth, makes you think a little more about it. So when I begin to think about things I might do on behalf of the new life in the way of developing environments that will have available within them the means for the child to acquire what it wants to acquire in the way of information, because that's what it's going after all the time, information. Couldn't be more after information. And absolutely nothing can interfere with it, with that information. And so that I like to have it, get it safely, yet not, I'd like it to know that it can't hurt. It's just like it's going to hurt you. You got to have some feeling about what that gravity does. But I'd like it not to know it gets hurt, but not so you're going to be done away with. You're going to get damaged, you know, the equipment damaged. So I'm sure all those things are designable. And they must be thought of in this kind of intimacy. Now, something I've just gone through something very simply with you here, but this brought me to an awareness. Because the touching is already operative, I find all the other faculties are rated in the terms, relatively, of the touching. So you say it is feet away, touch. Distance is feet. Feet or hands high and so forth. That's why man began talking. And I find then that all the things he does is rated back again to the tactile. That's it. That's the big one. To such an extent, here comes to me really a shocker. I find that you only see what you could touch. You don't know me by what I'm saying. You don't know me by my hearing, what I'm smelling. You know me by my touch. The dog tends to know me by my smell. But we just absolutely take the absolute limit case that you only begin when I can touch you, which is exactly which is not you. Now I say if and he may be, it could be that Democritus is sitting here with us, but every time I say the word atom, Democritus is here. He invented the word, he had the conception. Democritus is absolutely immortal. As long as you ever hear the word atom, there's Democritus. So I say, what we really are, if you had been really paralyzed on your tactile when you're in the womb, then you would probably begin where you smell me. And maybe a shorter time in the womb of a dog then makes it want to be much more smelling. You understand? But the point being that also then if you've been tactilely paralyzed and had no smelling, then I would be where you hear me. That's actually what I'd be. And if you'd had the other three paralyzed, then I'd be where you can see me. And what you would see would be something very, very different, I'm sure. You'd probably see my emotions rather than what we really be, I don't know. But this really gave me insight on how incredibly, really, as very beginnings of things we really are in our apprehending, that we continually come back to the tactile. To such an extent, we put on special clothes or whatever it is, just make it look different. Put on a mask, and the child comes around, and there's no question about it, those masks are very powerful. The Africans learned it long ago. The mask is a mask. Boy. I'd like to come back to pictures. I ought to have something I say after I say come back to pictures. Now, we're looking at you remember I gave you degrees of freedom, where there was myself in the universe. I think if that could be put sideways, could that be put sideways? So, because it's only showing two, and there are, I think there are 4 frames. The top one is where you are just the tether ball, and now it'll turn sideways, and you'll see it where there it is. The tether ball is way on the left. Then the next one, you see yourself in a plane, where the three make a plane. You can find that you move. You're looking at the degrees of freedom, and you're allowed to you can make a plane. And I'm sorry to say the tension line is, gravity is to your right, so that the gravity is pulling the thing sideways, and the top ball you can see is free, and then the next cartoon you can see the ball moving around in the plane, as it did in the middle of a music string. And the third one, you can see it moving only in a line, so it doesn't in the middle of a drumhead. And the fourth one, you see it immobilized as far as locality goes, but in order to prevent it from wriggling locally, rotating, then we had to have finally the 12 restraints. The next picture, please. Would you remove me? I've got here a water spout. The upper one there is a tornado or water spout, where we get the airs get disturbed and they get rotative, get a thermal, and all air comes, like all ropes, they always twist. The thermal is twisting, and gradually it gets sucking so much that it pulls the dust into it. It is absolutely invisible until it gets the dust into it. What you see with a tornado is everything is sucking up there. It's just loaded with debris. I've also then taken that funnel twister and put a knot in it up there on the right upper right-hand side. Then the next one, I have 3 twisters or 3 water storms, and they're twisting to make a piece of rope. I want you to realize that what goes on with this twister is that it finally sends out, and it comes back in itself like this. It's finally to be an apple shape. It's our friend involuting and evoluting. It's evoluting at the top, and it's involuting at the bottom. Because the air is being exhausted this way, automatically pull rushes in air in to satisfy it. So what you're looking at up there now, the lower left, you're seeing the beginning of the bomb, bikini bomb, where you can see it spreading at the top. And the second one, you see the rolling donut, and then you see the third, the middle one at the bottom, is the electromagnetic field, or be the magnetic field around our Earth gets to be this kind of a form. Now, we're looking at the reality of those electromagnetic fields here. Very extraordinary, the space picture of it. Next picture, please. Now I'm saying this is the atomic bomb. It's starting to spread, the mushroom. The next picture. This next picture was the cover picture on Life with the first bikini atomic bomb explosion. And this amazing one comes out. It's a geodesic dome, and you'll find it again. It's coming out. It's one of regular geodesics, and it is a 3-frequency geodesic. As this thing finally gets really shaping itself towards the sphere, then suddenly these are the least resistance forms. Very, very exciting. Next picture. What we're looking at here, you can see, is highly geodesic, and it is the model made for me by one of the early virologists. This is the polio virus. and it is strictly the icosahedron. This man was a physicist at the Boston Children's Hospital, and he now works primarily with the Cavendish Laboratory group. Next picture. Now you're looking at something else that's kind of look kind of familiar or kind of geodesic with the hexes and the pence, and because we get those kind of spaces. And what you're looking at is the actual fibrous web in this is the eye, an eye as a bull, as the eye of a bull. Also, incidentally, the bull's testicle comes out exactly the same pattern, but all the eye structures are this way. These are the eye structures. I want you to see, it's fantastic how these suddenly things show up. And as I get more and more scientist friends who are interested in, I'm saying this was sent to me by a Viennese biophysicist, and he realized how interested I'd be. Next picture. Looking here at pictures, if you could remove me again from the picture, what we're looking at is pictures made of the radiolaria. This is when the voyaging of the British scientific ship and the Darwin went on and so forth. These are pictures of the sea life, and we have these particular ones are radiolaria, but we have also the diatoms tend to be in these same kind of forms. Next picture, please. And incidentally, look at what you're looking at are the central angles of the tetrahedron. This is the one I found I could not make with great circles fold up. And incidentally, just remind you about those great circles, that there were 7 great circles that were foldable, and they all had to do with the energy bank either going through space or cutting it off in local holding patterns, and there are no others that can be folded. This is a limit case, there are only 7. And they all have to do with this basic symmetry. Now, next picture. Here you're looking at some more of the radiolaria and the algae. These are not the algae, and the diatoms. Look at the octahedron and the really very beautiful thing. Would you remove me, get me out of the way of this array, because it's ready to remove my picture. I want you to see in the lower left-hand corner there's the dodeca, and there's the octahedron up the upper left-hand corner, so it goes the tetrahedron upper right. They're all there. And then we get these sea life, absolutely the simplest things coming together in the simplest ways, and this is where they go. Again, this confirms what I want you to do, get the very simplest, and here we are. Next picture. Now, we've got a stack of ping pong balls with a red ping pong ball on the top. And I spoke to you, I'm going through pretty much what I went through with yesterday, but there's going to be more added to it each time. I want you to be really very familiar. There's one red ball on the top. In other words, it is the only potential nucleus that you and I can be looking at. Let's take the next picture, please. And it'd be a good idea if I were out of the way for these pictures. I've just taken off the top tetrahedron, and you can see the 6 balls at the top with no ball in the center, right? Next picture, please. And eliminate me again. That's fine. So then you see, I'm now down with the 4 balls to the edge. It's a 3 frequency. There's a new nucleus showing for the first time. There's the first red ball on the table to the left. Then the 2 layers that have no ball at the center. Then the 4th layer has a ball at the center. Next picture. Now no ball in the next layer. 5 layer. Next picture. No ball again, that one. Next picture. Next. Then there we suddenly come to, so I said, it's a yes, yes, no, no, yes, no, no, yes, no, no, all the way through. And these are the fundamental distances that make the fundamental distance between nuclei. And that yes, no, no also has a great agreement. Remember when I was spinning the great circles yesterday, the red yes, no, no, that happens very, very often. And where we get to the nature's taking one out, remember by giving you going from the octahedron to the 3 tetrahedra face to face. I think I'll do that again because it is worth our doing at the moment. Here's our octahedron, absolutely symmetrical. It's generalized. It's very much in the middle because tetrahedron is a minimum case. Icosahedron is the maximum case of structural system. It's a middle one. And we find it has a tendency to be doubled up. It also really has a storage of, it's that fundamental two-ness of universe, they're all in one. And so we're having 2 extremes, but it is the middle, so it's 2 or something. And I'm going to take one out, one vector out. And just taking it out momentarily. Now I'm going to put it right back in, but I'm going to precess it. Remember, precessing goes like that. So there's a precessing effect on it. And so it goes in here, it goes in here. And what we have now are triple bonded tetrahedra. 1 tetrahedron here, 2nd tetrahedron, a 3rd. So the volume is 3, and the volume was 4 when it was octahedron. So you're literally annihilated, but all the energies are here, because the energies are the edges, are the vectors. So I want you to understand how this is all there is in the universe, and physics about annihilation. But the interesting thing about it is then also then gets to be the beginning of the tetrahelix. So we're going from the generalized immediately going into the special case. It's a very, very exciting realization. Okay. Next picture, please. Next picture. Now you see up at the upper right the 2 red balls, and there are always 2 layers between them. And what that makes, quite interestingly, is 2 tetrahedra, but 2 tetrahedra made of balls rather than, so this behaved differently, you see. If they were planar, they could come face to face. But these don't do that. The balls nest, they go this 60-degree precession. So they're the 2 red balls, and what do you have in between? 6 balls, and those are the octahedron. So these 2 red balls is an octahedron. There's a basic symmetry between 2 nuclei, 2 potential nuclei. That's all that is saying. And it's interesting because it is not that kind of tetrahedron, it's this kind of tetrahedron. It's a nested tetrahedron. If these 2 were joints, they would come together and you wouldn't see them because they would become congruent. As they would bond together. Okay, next picture. This is a repetition of the 1 ball, the 3 balls, the 6 balls, the 10 balls, and so forth. Next picture. And this is a little review of thinking about, instead of calling it nucleus, I called it the ability to nest. So that one case I'm talking about positively, this is a new nucleus showing up. On the other hand, there's an advantage of being a space where you can nest. And it begins with the tetrahedron. 2nd is the 1/8 octahedron. The 3rd is the 1/4 tetrahedron. So these are fundamental increments of universe, as really actually spelled out by fundamental just associability. That you feel much more comfortable about using quarter tetrahedron and really looking at things that way once you discover that so. Next picture. Now I've got 2 balls on a wire, and other 2 balls in a wire. And I want you to see what they are doing. They are remote from one another, the pairs. May I have the just picture? You can leave. No, you want to put me in this picture. I got. What happens to these 2 balls is that near each other, and the effective motion is they precess, so they do this and they do this. Realize how one half the tetrahedron is really precessed to the other half, the pairs. Linus Pauling does a great deal with these kind of spheres, and I said he's a Nobel Prize chemist, and we'll see some of his models after a little bit here, and they do relation. And he said, because the numbers of the vertices in the universe do come out evenly, all the sphere agglomerations in the universe can be divided into pairs. They're twos. Universe can be divided up into fundamental two-ness. So there is a multiplicative two-ness, and the additive two-ness is a multiplicative two-ness. So this one sphere, it's inside this and outside, and you see both at the same time. Next picture, please. This is when the two balls just come together precessionally. Next picture, making the tetrahedron. Next picture. Now we see 3 balls in a row, and 3 balls and 4 balls. I'm going to make a model of this. And don't go any further with your picturing for the moment, because I'd like to make this model up for you with my pens and the spheres. So here's 3 in a row. I talk about nuclear phenomena, how different patterns obtain at different levels, so that I get the 2 balls as precessing, and say, that's very simple. Everything else must do that. But I got a 3-ball, couple of sets of 3 balls there. I'm going to have to make a pair. And you make another pair. Got 2 pairs, but this time I'm not going to precess them. I'm going to... They're not in the precessing part of the story. So I'm going to run one pin perpendicularly there, another one perpendicularly. I'm going to make them into a square, which would not be valid if they were all by themselves, because the square wouldn't hold its shape. Now, we have that precessing is something to do. Tetrahedra tend to precess. So I find that what happens here, this wants to do this, but it just would roll around on here, it wouldn't be stable. So what do we have, and this is here, and this one's here, now it goes like that. So then there's a 3-ball tetrahedron. Once you see how this precessing is then accommodated by the square in the center. That square is also then the cross-section of the octahedron. It is at the center of the 4 tetrahedra. So it's getting into an octahedronal kind of a condition. In fact, if I took all the 4 balls away from the 4 corners, you find you have the octahedron sitting in there. That's really quite different from when I put a 4-ball edge there, that vein, and there were 5 tetrahedra. But this one has the octahedron in the center. So things are coming out quite differently in different layers here. As the frequencies exchange, something unique is going on. Now the next one I'm going to do for you, you're going to be able to see in the picture. May I have the next picture after the one that I had last shown? So there you see the 2 of those that came together. So if you can, and if you could turn a little bit, get away from each other so that our camera can look down at what you're doing. Four in a row. Now you got your 6 here put together. Fasten those to your 4. put down the 6 on the ground, and let the 4 sit on top of them. Now pin those together. And you want to make the same thing. You want three pairs, and then make them into a raft. Find some way to pin those. Clever.
Excuse me.
Let me have it. It needs a little bit of a which is the loose end? See if we can pin there. Good. Now, I have had a very interesting time with these particular pieces in the past, and young ladies will get up and go back to their seats after they give me the 2 sets here. And when they do, then the cameras can get back into more normal array. But here is a component. Now, I have made this model many times, and at, well, you know, universities with the top universities, say Dartmouth, whatever it may be, and I've had the top mathematicians and so forth, and I've given them this to a mathematician, and there's another one just like it. You've been with me now so much you know what to do, but I just give these 2 items, and particularly if I make it paper. If I make this a paper, in fact, I can't make it paper, I can only make it the balls. So here are 2 of them, exactly the same. I say, put those together. What he said, he's got to find something symmetrical, so he finds 6 and tries that. Yeah. Or you try this like that, doesn't seem to do anything. You just, because the 6 are a rectangle with completely different dimensions, there's no reason in the world why you would think any way to put them together except by the 6ness. The way people tend, because they think 90-degreeness. They don't think 60-degreeness. 60-degreeness is always convergent. They're thinking parallel motions. So what you do, again, is cross precess. There's this lovely thing. So 6 all right, but they converge. I find human eyes just don't think that way. I really had very distinguished mathematicians, and they never catch it. My grandson and I were, he accompanied me for a whole year around. We went to 50 different universities last year. And we were at Rhode Island, and there's a little girl, the professor's daughter. She was getting quite good at school. She was about 10. And I gave her a model of this. We had to leave. And she couldn't get it. So I showed her. My grandson said, Grandpa, you cheated that little child. I said, you never get. This is what you got to find out for yourself. You had given her the challenge, she would have found out, he said. And you cheated that child the right to find out. And well, if you did find out, then you'd feel the 60-degreeness. You'd have to explain it to yourself if you found out for yourself. But just telling it like that, you'd lose the whole beauty of it. So this is one of my most beautiful lessons I've ever had. Still part of that, how to get on with the child. But I was amazed how my nonsense as an older man, wanting to feel gratification. I thought, really, I want to be big. You show off to the kid. So, the big thing is here the 60-degree convergence. Everything is converging and diverging. That's the way nuclear things are. They converge and diverge. They don't parallel them. And all of humanity keep working on parallel lines and cubes and squares. That's not the way the universe is. So when you begin to think convergent, divergent, then things really fit. Now, next picture, please. Now, there's the one I just put together. Next picture. Now you see a really very big one. This is a very exciting one. They are, count the edges, 1, 2, 3, 4, 5, 6, 7, 8. That'd be 7 frequency. Next picture. Take these two apart. There they are. And the two parts are hollow. And they're very strange. This is even more provoking. When I make this one up, it's so big I don't want to try to stop you to do it. But there are in each half there 50 balls. So the two balls coming together have exactly 100 balls. And I find, because they are hollow, they do really surprise people. Now, what they have inside is exactly room for a 4-ball edge, which is a 3 frequency, just goes inside. And it has, we may remember, exactly 20 balls. When I put these together, 4 times 5. What fits inside the one that's up in the wall is 20 in this, and the enclosure is 100. So I could get, and we know there's no ball in the center of this group. Remember, there's a tetrahedron there. It's a sphere, centered absolutely space. So a 20 ball is an absolute space in the center. So I can get 100 on the outside. I can get 120 balls around a common vacant nucleus. This is the largest number of balls I really can do. Now, the next thing, if I want to have a nucleus, then I'd have to put one more layer on the 120, and then you suddenly have a nucleus. Next picture. Now you see something else rather interesting. You remember that I showed you the nestability of the tetrahedron. Can I have some more nest? And we just kneel right there down so the camera can look in on you. This camera can look on you, but do it out in front of you where the two cameras can look at you. And I can make a 3-ball edge tetrahedron. No, 3-ball edge triangle, that's all. That's it. All right. Now, that is nestable. So fasten that one in the center. I'd like to make another one of the same. You could speed up by coming up possibly. I'm trying to keep these things where camera can see what's going on. I'd like another one of those made. Would you go back and somebody else try it? Who hasn't made one? Just leave it on the floor, dear. We'll make another one just like that. That is the second case of nestability, remember? I told you it is a 1/4, a 1/8 octahedron. And if you're making 1/8 octahedron, you find sure enough the angle is exactly right. And listen, when you do, you think, would you keep yourself turned a little this way? You move back over towards this way, and then you be right. So your hands will be out on the floor where both cameras can see it. Rotate a little more, dear. Good. Work out towards your right foot more. And put your hands further out. Try to keep, I'd like you to keep things in the picture so everybody can feel it. Enjoy it. And I put one on top of it. It falls by itself, then. Okay. And fasten it in there. Just fasten it. Then I'm going to ask you to do something logical with these two pieces. Just a minute. Something that feels good to everybody. It should come down just a little more in the nest. Yes. I want you to do something. Would you turn a little more away from me, dear, and so that everybody can see what you're doing? Does that feel good to you? We've been talking about precession. How could you precess? What could possibly match there? You match the little faces of the tetrahedra. Push the central balls down more, both cases. That's it. That's it. Somebody else want to try? What else could you match with the triangular faces? Come on. We got it, young man. Will you turn around, old man? You move down, and you come in here. I'd like the camera to see what you're doing. Don't take them apart.
Same thing.
Now, let me tell you, when you finish, you'll know you're right.
Next.
Now, don't try to dislodge that central ball. Keep it in its nest. Keep pulling together a little where they tend to get coming apart. Now, I just mean the one by each. Keep each one in as neat condition if you can.
Am I close? Was I close? No?
You get so close to it that it makes me. I bet you see that. Keep it around where the camera can see it, dear. Precess. There it is. Put it down on the floor. It's a cube. You got it. These pins are bad. Come near me. I'll fix the pin in there. This one's done. That's a cube. Beautiful cube. Just put it down on the floor. It's a cube.
I didn't even recognize it.
That's because those angles, remember, were the right angles. It's a quarter, and 190 degrees. No, it's not. It's 1/8 octahedron. So 2 1/8 octahedron give you the cube. They will not do it just by themselves. In planar, they will not do it this way. They got to do it only in the balls, the vertexes. Next picture. That's going to be up in here in the show. Now you see a big cube. So there are big cubes, and you find on each corner of the big cube is one of those 1/8 octahedron. And it is a big cube, those corners been put onto a vector equilibrium. Next picture. There's a vector equilibrium. You're taking the 1/8 octahedron off of the corners of the cube, and that is your vector equilibrium. And it is a count the number edges. 1, 2, 3, 4, 5 is the 4 frequency vector equilibrium. That really is the limit case of the nucleus. I'm quite certain that you would get into the post-uraniums because you get outside of the 92 because there's still, this arrangement still is a nucleus. Next picture. Now you're looking at an icosahedron made out of balls, but you cut the balls so they're down to the planar side, so you can see what the balls look like together. That's the icosahedron where there's no ball at the center. Next picture. Now, I'm sorry to say that the pictures are not sharp enough, but the top and the bottom, they're now looking at a 3 frequency. It's icosahedron, but it has a white, there's a different color, but you'll see when you do the counting, whether it's vector equilibrium or it is the icosahedron, you'll find if you cut the balls away like that, the pole ones, the +2-ness is quite clearly as a different color than the others. The other faces get together where I give you 3 come together with 2, with 1 or whatever it may be, but you'll see all the triangles coming together, giving the second power area. But the numbers of balls in the outer layer will be frequency, the second power, and then the poles of +2. And you always see the balls are right there. The count is there every time. It's a really very beautiful thing. Next picture. These particular models are supposed to show it to you, and somehow or other they faded away. You can see the icosahedron there. This is where you get the multi-frequencies, and I want you to understand how well they work for the single, just the plain tetrahedron, or where you see then 30 faces to the 20-face icosahedron. They break into 10 diamonds. Remember how the diamonds then complement? So you're looking at 10 diamonds grasping each other here, of blacks and whites. Plus always 1 extra north pole, 1 extra south pole. It's a lovely thing to make the count. Next picture. There it is, that's vector equilibrium. And the poles have been identified there. Next picture. This coloring is really quite badly faded. That's the same one you saw as vector equilibrium becoming the icosahedron. But it cannot have any layers inside, or it would not be able to collapse into it. So no matter what the frequency is, it has to, the icosahedron closest packed surface, it can only be 1 layer. And I'm quite certain this has to do with its electronness. The icosahedron's electronness cannot have the nucleus, but it has the same count as the vector equilibrium, which is the nucleus. Next picture. Could you put it in so that I guess that's all right. You're looking at pictures made by Linus Pauling, or rather models that he made, and from his Nobel laureate book paper. There you see, one of the things he does, where I take the vector equilibrium, and he takes the top 3 balls and rotates them. Because remember, there's 6 nests up on top here, and we only use 3. There are 3 alternate ones that you do. The minute you rotate, the top band becomes polarized. It's absolutely omnidirectionally equilibrious until you take the 3 top and rotate them, it becomes polarized. And when you polarize, take the 3 top, so you get 12 balls, 3 balls at the bottom, 3 balls like that. Then you get around the equator, you get pairs of squares, pairs of triangles, pairs of squares, and then a triangle and triangle on top. So that it is completely polarized, and when you make a section through the polarized vector, what used to be vector equilibrium, is no longer equilibrium because it's polarized, then cross-section of it is the chemical hex. So I want to bring you in some proximity with other phenomena that because all the hexes have to do with polarization, where things, I said, You never will catch nature in that vector equilibrium. She's always going to be in the polarized. She's going to be always offset one way or the other. Next picture. These are more of Linus Pauling's pictures. Next picture, polarized sets. How he can bring together threeness in various, but they're all polarized. Now, the top one is a vector equilibrium, and it's got a red ball inside, and you knock the red ball out of the center, and comes the icosahedron. You make a rubber model like this. You just have them fastened together, rubber bands, pull the one out, and they immediately snap in the vector equilibrium set. The icosahedron. Next picture. Now we're looking at the three on the top, which you do rotate. Next picture. To go, I want to show how, from the polarized to the vector equilibrium, just rotate them. Next picture. Now we're beginning to look at a little larger vector equilibrium there are four balls to the edge, so it's a three-frequency vector equilibrium. And then notice then there's a triangular face towards us, and there's a red ball at the center. There's a new nucleus beginning to show in the 8 faces, but it will not be a nucleus till it has its 2 layers around it. So, but this is the one that has 92 balls in the outer layer that I gave you yesterday, 42 in the inner, and 12 in the innermost. Remember, I gave, next picture please. Now I've opened that up so you can see all the different layers as they come together. And these balls have different colors when the amount of light that they get from the nucleus are different. So I've talked to you about trying to find a nuclear set of events that would repeat itself. And so I get absolute uniqueness for those first 3, 4, up to the 4, and the 5th begin to get something repeating. But these colors relate then to the amount of light or radiation available, or the traction from the central nucleus to any given layer ball. Next picture. You can see on the top one, the corners, 12 corners, are always direct contact where the light goes right through them. Next picture. This is a picture taken through one of my models where I've used the beads, which Mehdi found over there the other day. They're lovely, lovely beads that were developed during World War I, and very uniform radius, and they're glued together. And I used they're all transparent, but some of them are colored. You're looking at the vector equilibrium. Remove me now, so I'm not in the way of the picture. And I want you to see what really quite extraordinary kind of thing. The bright white lights of the 12 corners, you can see how they go. This is simply giving, there is a red at the center, because you'll sense what I mean by the relative amount of light that can come through to different balls in different positions. And this particular model, you find an enormous agreement with much of the light emission microscope kind of things of atoms. Next picture. Now, I spoke about spaces between spheres. And here's a tetrahedron. Wait a second, will you have the picture still? I'm doing this so you can really look at the picture on the wall, because it's well done. There's a space then inside here. And we know, what do we know about it? Well, it's got 4 balls around it. If I made this out of ping pong balls and glued them together, then I took a safety razor and cut away everything except between, we'd find then there's a little triangle, a concave triangle up at the top here nesting down, touching 3 others, making the, would you remove my picture from here? Over the left-hand side there, you'll see them coming together. There are 4 triangles, and there are 4 spaces, therefore it's the octahedron. But it's a concave octahedron. So the center of the tetrahedron, there are concave octahedra. And I'm going to make an octahedron is made really very, very simply by taking So the fundamental way to do it Ow. But again, in a hurry, you try to pull pins out. It doesn't pay. 3, and let me take 3 from here. Can't do it. Thank you, sir. All right. Here are 3 and 3. I found precess, and because the octahedron. If I'd done that before you did the cube one, you might have thought of it. But there's your octahedron. Now the octahedron then has 6 balls, and you see a square section. And you remember then how when we made the 3 balls, it had a square section, and you really feel those things. And so there's 6 balls, and they make a square section. So when the 6 balls touch each other, each ball touched each other with a square section. See this top one here? If it glued in the ping pong ball, and I cut away everything, it would leave me a concave square. So there's 6 concave squares where the 6 balls are. That also then there are 8 triangular windows because there's the octahedron. So what you'll have then, next picture, will be the vector equilibrium, the concave vector equilibrium, with the 6 triangular concave squares and the 8 triangular windows. These are all the spaces there are. There are only 2 kinds of spaces between closest back spheres: concave octahedra and concave vector equilibrium. And they are pretty interesting because you start with a vector equilibrium and it goes down to that octahedron where the things double up. So it looks like, could be that the openness doubles up to itself, to its octahedron in its own spaces here. Something to do with that. Next picture, please. Now I'm going to take, there are other pictures of these. Here we're doing that in a really rather open frame, so you can see the vector equilibrium with its triangle, the octahedron on the left, and the concave vector equilibrium on the right. Next picture. Now we can see 2 vector equilibria coming together with one another. I showed you the square faces come to one another, and that there's an octahedron between the 2. Remember that? That then left a space the outside for, so there's external and internal octahedron in relation to the vector equilibrium. Next picture. Now, what you're seeing there are a number of the actual ping pong balls. In the lower right-hand side are the concave octahedra. In the lower middle right side are the concave vector equilibria. So you put the little triangular windows of both together, making the edges match. And together they come to make then fill all the space. But you get a set of an aggregate of balls where you see the convex surface outside. You see only the concave side. This looks very much as if, I don't know whether you must have done it, picking up fossils where clams have been fossilized into clay, and the clam died in between, so the 2 clam shells come apart. So what you see is the concave side of shells together in the clay matrix. That's what it looks like. But you keep putting these together, and they keep filling all the space. But the outer group will always be in the concave side. So what we're now seeing is really very interesting. There's some relationship between spaces and spheres. And remember that there were nests that you didn't use because the aggregate of the 3 only lets you use one set of the nests at a time. There's an alternate set of nests, which are also then the spaces that are in there, and there are 2 kinds, the octahedron and the vector equilibrium. Now, next pictures. I'm looking at an aggregate here of vector equilibria plus octahedra, where there are octahedra, the external octahedra are put in between the, on the outside triangular faces of the vector equilibrium, and the interior octahedra go in between the two square faces. You're going to see some more pictures. Oh, next picture. That is a vector equilibrium with the four removable, borrowable spheres in the four faces, which is very, very important to chemical compounding. Next picture. Now you see red vector equilibria and a white, you see a white octahedron, which is I said, this is the external octahedron, which nests down between any four, because they're triangular corners on every vector equilibrium, and when you bring eight of them come together, more or less cubically, and they have an octahedron between them. Next picture. Now you're looking at red. I'm sorry to say there are red-yellow ones, and there are white ones. Every other one of those, one is where a sphere is going to be, and the other where is a space going to be. They could all be actually cubes, and you stack a bunch of cubes together, as you know you can, close packing. But if you then realize that where the corners of the cubes come together are where the external octahedra are, and where the faces of the cubes come together are the internal octahedras. That is a pack that you are looking at right now, but I want you to realize then you're going to find in closest packing that the arrangement of centers of spheres and centers of spaces is this arrangement, where you're going to suddenly discover that the vector equilibrium, I gave you originally vector equilibrium flat, remember, and then I gave you where you curve the edges, where it came convex, or it couldn't be concave. The same vector equilibrium that can come concave, or it can come convex, and so can the octahedron. So we have then spaces that suddenly become spheres, they blow up, and the spaces contract. So terribly exciting going on here. Next picture. Now you're looking at, when you remove me again, you're looking at I made a frame, a steel frame, it's a cubical frame, and there are brass rods, wires that run with a cubic frame. I told you that the perpendiculars to the faces of the vector equilibrium are the same as the perpendiculars to the four faces of the tetrahedron, which is our basic system of all. If you run there are 8 corners to the cube, and so if I run a line from one corner of a cube diagonally down through the cube to the opposite corner down the floor, I get then 4 diagonals for the 8 corners, and they are the lines that are perpendicular to the faces of the tetrahedron, or the 8 triangles of the vector equilibrium. I've now mounted in there, you remember how I made the jitterbug. And the jitterbug then, remember, can go from being open as vector equilibrium, it can become octahedron, and what you're looking at, I put little transparent plastic, they use plexiglass, red triangles and white triangles. And I've mounted them on the rods. Could you go back to the picture itself now? You're going to see there are 8 octahedras showing there. But if you look very carefully, you're going to see some white or clear sheets. Those are the